That's circular function trouble. All right, so let's see if you remember anything. I want to focus on the important ones. No. What's the summary for the NOR gate? 1 is always going to be at 0, right? What about the NAND gate? 0 will always be at 1, right? And well, XOR. Right? Once the outputs are opposite, 1 and 0, you'll always get a 1. All right? So we need to remember those gates, right? Nice. So from this now, we can start to build on the applications, right? It have 3 main applications of logic gates that we have to look at. We have to be able to do the adder. We have to be able to do the bistable, right? There's like the flip-flop. And then we have to do the T-type. All right? These are the 3 applications of the logic gates, right? So we have to be able to do those things, right? So let's start with the adder. Well, let's see everything, right? Right, the first thing that we have to take a look at is the adder. So in order to understand the adder, we have to be able to add, right? We have to be able to do addition. So let's see if we can add these things here, right? Right. So if you had to add 1 on 1, 1 on 1 and 2, right? And 2 in binary is 1, 0. That's okay. 2 in binary is 1, 0. So 1 plus 1 is sum 0 carry 1. So if I give you a binary addition that looks like this. Yeah. So that you would see that 1, 1 is 2. Right? What is 1 plus 1 plus 1? 3, right? 3 in binary is what? 1, 1, 1, right? What is 1 plus 0? Right? Sum 1 carry 0. If I put it the next way, it might look like 2. Right? So that's why I put it carry first. Right? 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 is 0. All right. So that's why I put it like this. So you should remember that 1 plus 1 is 2. 2 in binary is 1, 0. 1 plus 1 plus 1 is 3. 3 in binary is 1, 1. That's okay. And I'll show you the sum and carry here. So watch this here, right? If you're adding in binary, 1 plus 1 is sum carry 1. That's okay. 1 plus 1 is sum 0 carry 1. The sum comes here, the carry goes up there. Right? 1 plus 1 plus 1 in binary is sum 1 carry 1. That's okay. 1 plus 1 plus 1 in binary is sum 1 animal carry, so you bring it here. That's okay. So that's the way you perform addition. Binary addition could be done by making something called adder. Right? So to perform this long addition, we need something called adder. Adders are made up of what? Adders are made up of a half adder and full adders, right? Right, so in order to make this adder chip, that's a chip that will do the full addition, we need a half adder. I just drawing the block diagram here for the adder chip. You need a half adder, a full adder, and a full adder. Right, I'll go through each one individually, that's not right. But if I wanted to make this full addition, I need these 2 chips here. That'll make up another chip. So you have the inputs here, inputs here, inputs here. You have your sum here, carry going here. Sum here, carry going here. Sum here, carry. Right? So if I wanted to perform this addition, I need this. And I put in the 1, 1 here, 1, 1 here, 1, 1 here. That's okay? Right? And that's it there. So that'll be a sum, carry, carry, carry. So this is added chip, right? This full thing here is added chip. So what's the half adder made up of? If you look closely, ignore this row here. If you look closely, this is an AND gate. And this is a what? An XOR gate, right? So to perform this whole thing here, we need an AND gate. 1, 1 giving you 1, right? We need an AND gate. So the sum is done by an AND gate, and the carry is done by an AND gate, and the sum done by a which one? XOR. The sum done by an XOR gate, right? So half adders is XOR gate and AND gate. Right, these are your two inputs. Right, this is the output, sum, carries. What's the full atom made of? Right, you'll still remember it, right? Once you can produce this, there's an AND gate and there's an XOR gate, right? And then you just draw them here and connect it up. That's okay? What's the full atom made of? Two half adders and a two half adders and a OR gate, right? Right? And a adder chip. Right? So you have a half adder here. I'll draw the block diagram. This is in here. You have a next half adder here. This is in here. And you have a OR gate. Right? Your two inputs go in here. Your sum, the carry goes here. Your sum goes here. And your previous carry does this here, comes here. Then you have your sum. And then you have your carry. Right? Let's just make sure we understand how to use it. Right? If we were to add 1, 1, and 1, we're supposed to get 1, 1, 1 is supposed to give you 1, 1, right? Let's make sure. 1, 1 into a half adder is what? Sum 0 carry 1. That's okay? 0, 1 into a half adder is sum 1 carry 0, 1 into OR gate is 1. So we get the answer, right? Right? And if you take this full adder, put it here, this full adder, put it here, and this half adder, put it there, that'll give you the addition. Right? Right? This will do 3-bit addition. So yeah, if you need to go to 4, yeah, add on 1 more. All right. So this here is the first application of the gates. Next is the one that we all like, price table. Right, copy down what you need. Have everything all right. Okay. And you feel that on there will be about they don't want to take all together. Right, the master but I don't want to keep saying it. All right, next one. The next one is the bistable, right? Anybody remember an application of the bistable? What's the most popular application of the bistable? Well, it's a flip-flop. Like what? I don't know application of it. Alarm, as an alarm, right? That's the most popular application, right? Right, remember there are two types of op-amps. Sorry, there are two types of bistable. One bistable is with no gates, and next bistable is with NAND gate. Remember how it's not? It's not over, right? Right. So bistable, I will do the no version, the NAND version, the same thing, right? It's just the outputs to be opposite, right? So the flip-flop of bistable of RS flip-flop, the RS flip-flop basically looks like this. You have two NOR gates, right? You have two NOR gates, and usual thing, you have the two inputs, I1 and I2. Here you have Q, and here you have Q hat, right? This whole system works, right? This whole system only works or only functions when the outputs are opposite. If the outputs are not opposite, it's not stable state, right? So this output is this input, this output, this input. All right? And it's real simple how it is work. Right? It's real simple how it is work, right? So let's take a look at 1, 0. For a NOR gate, a 1 will always give you a 0. So once I have a 1 here, I'll always get 0 on the output. So it doesn't really matter. It doesn't really matter what the input is here. A 1 will always give me a 0. All right? A 1 will always give me a 0. So 1 gives me a 0 will come back here. 0, 0 into NOR gate is. 1 will come back here. 1, 1 gives me 0. So it's stable. These outputs are opposite, so it's stable, right? That's okay? Right? And here's the important stage. The important stage here is that if I were to take off that 1 and put a 0, if I were to take off that 1, right, and put a 0, what will happen? 0, 1, still giving me 0. 0, 0, still giving me 1. 1 coming back here. The output not changing. So by changing this to 0, nothing happening. Right? The output staying as whatever the previous output was. That's okay. That's called save or latch. Right? So by changing the input from 1, 0 to 0, 0, we were able to save it. Are you okay with that? So for the NOR flip-flop, 0, 0 will save. Right? Whatever your previous output was. For the NAND flip-flop, 1, 1 will save. Right? Same principle. It'll be a little bit opposite because it's NAND gate. Are you okay with that? What would happen now if I change this 0? If I change this 0 to 1, what I could do there is I could switch my outputs, right? I could flip it. So if I put this here, 1, 0, 1 always gives me a 0, 0, 0 will give me a 1, 1, 0 will give me a 1. So basically, 0, 1 giving me 1, 0. Right? So I'm able to flip the outputs. Right? From 0, 1 to 1, 0. And then what would 0, 0 do? 0, 0 will save the previous output. Right? So one of the popular uses of this is in a security alarm, right? So you have an alarm set up and the burglar tries to open the door and the 1 goes to 0. Right? And that will set off an alarm. The burglar now, he set up the alarm here. Right? And by setting up the alarm, he tries to close back the window, but closing the window saves the last output. See that? So if you look here, right? Right, the window was closed, everything was the security system was off. Right? Let's say here, the security system off, both windows closed. If now the burglar open this window, what will happen? If he open this window, he will now flip the outputs to go 0, 1. And if I connect the alarm here, the alarm will go off. Right? If the burglar quickly tries to close back the window, the alarm will still go off. All right. The only way to take off the alarm is for the owner to come in and set back this 1. Right? This is probably that's probably the switch. Okay with that? Right? So this is the application of the price table. One thing I want you to know as well is that this exact thing will work, right? If I just convert to NAND. If I take off this and I use NAND gates, all you have to apply is this. 0 always gives you 1. That's okay? So you have your NOR flip-flop and you have your NAND flip-flop. And the last application is something called T-type. Right? The T-type looks like this. It's a box diagram split. It will give you a Q, right? And Q is the output, right? Right? And this is a triggered output. So it has different triggers, right? Triggers mean something has to happen in the input to trigger the output to change. So for example, I will use an upward pulse trigger. Every time the input goes from 0 to 1, it will trigger the output to change. All right? That's the way the T-type works. It triggers the output to change. So let's say the input is I1, right? Let's say the input looks like this. Let's say the input looks like that, right? How we figure out the output? Right? In order to figure out the output, all we're looking for, of course, the output might start at 0, right? All we're looking for, and that's why the first few to line up, right? Okay. Right. Right? Here's how it works, right? It has different triggers. You have to read the question and figure out the trigger. The trigger for my example here is every time a 0 goes to 1, it will trigger whatever the output was to change. All right? So here we have 0 going to 1, so it will trigger the output to change. That's okay? This is called an upward pulse trigger. It also have a downward pulse trigger as well. All right? So look at the input now. The input is going 1 to 0. I won't do anything. So it will stay 1. But here to here is a trigger, 0 going to 1. So it will trigger the output to move from 1 to 0. Right? 1 going back to 0, that wouldn't do anything. So it will stay 0. 0 going to 1 to trigger it. Stay the same, trigger, and so on. That's okay? So you will see the pattern every 2 changes. All right? Suppose now I connect this output, let's call that output Q1. If I connect that output to the next one, right? This output now becomes the input for this one. Right? What we're looking at to figure out Q2. Again, Q2 will start at 0. What are we looking at? We're looking at Q1, right? So we're looking for the upward pulse again, right? 0 to 1, trigger. So you're not looking here again, we're looking here. This is now the input to figure out here. This is a trigger. 0 to 1, trigger, right? So 0 to 1, triggering the output to change. 1 to 1, not triggering anything. 1 to 0, not triggering anything. 0 to 0, not triggering anything. 0 to 1, triggering it to change now. Right? No change, no change, no change, no change. Triggering it to change again. You'll see that? Right? Here's every 1, here's every 2, here's every 4. If you had a guess, Q3 is every 8. Right? And anybody remember application of this? As a binary counter. Right? Because it follows this binary pattern, it's counting in binary, right? 1s, 2s, 4s, 8s, and so on. So it can be used as a binary counter. All right? So the count, like if something coming in, cars coming in, first count will be 0, and then the next car will be 1. Just count, and it will show you a display. Right? So counter you use to count. Okay with that? All right, let's practice a few of this before we do some AC theory. Right now, there's zooming here for the first part. Right, we can do the first part mentally. In fact, there is do everything. Huh? I know. I just have all the questions dropped together. It's all the other folder thing. Right, we did all the research here already, so most of them is folder here. Huh? What's that? Next. Right? Part B, we just did it, right? So you can just write down the R answer. Right down the truth table for the XOR. Are you okay with that? Construct the truth table in B part 1 and 2. What was that again? Those 4 gates was a what? XOR, right? Huh? Part? Describing words the logic function of the circuit, yeah. Or do you just tell them it's an XOR? Right? Describing words the function of that gate then. Right? So that gate works as a right. You put C and D there. You're seeing D. Right, C and D pass. Right? What are you talking about in C part 1? C part 1 is what? Right? Using the XOR gate, draw the half adder. You okay with that? Yeah, the one I gave you here, right? The XOR and the AND gate, right? And show how the full adder can be implemented from two half adders in a circuit. Right, so part 1 you have to draw it, part 2 you have to draw it as well, right? Ah, part, yeah, see that? Right, one of the problems with these questions that you can't really get a graph on conjugation. That's one of the reasons why I've been up playing with this open question by itself. I guess we are right. Well, you can handle part 1 and 2, right? That's what I'm true for you. No, you can handle which one? Part 1 and 2 is what you on the board. See part 1 and 2. Right? Part 2, the one the block diagram, right? Actually, part 2, I'm gonna draw the circuit diagram as well. See part 2, right? I'm gonna draw the logic gates that make up the full adder as well, right? 24. And then part B, right? Show a block diagram to show the operation of that. Try that quick. You'll see it, right? Try down the addition of 110 plus 0.101. Write down the addition. Quick. And do the block diagram first. Right. Are we done? Are you done? All right, last 2 minutes. We have plenty to do. I start breaking about half past 12. Voy a algo, ya no algo. Voy a algo. I remember we do a order food. Everything is delivered is stuff 9 o'clock, right? Yeah, the order food. Remember delivery is close 9 o'clock. 9. I don't know. I need you right now. Right, time up. Let's see what he came up with. Right, the half order looks like this. Actually, yeah, I can do it like that because we'll have to throw it back. Yeah, that's a plan. That's a plan. Right, so that is your half order. Right, that's the half order, right? Now I'm gonna take that half order and turn it into a full order. Right? So I'm going to add a next half order here. Right? What we're gonna do now is connect it up, right? Right, so this will be an input 1, input 2, this one going here, this one going here, this will be your I3 or your previous carry, and then carry will come here, and you'll get your final sum, and you'll get your final carry. That's it, right? Half order, half order. That's C part 2. I draw the circuit diagram. What's up? No, in that question, they accepted the block diagram. Right? Yeah, but I just draw it for you in case they want the circuit diagram for the full adder. Right? I just draw it for you in case they want that. In case they ask for that. Right? So the block diagram is okay for this particular part. But in case the question says draw the circuit diagram for a half adder, that's what you do, right? Just draw the half adders and then connect them up. All right, and the last part is what? What we have to add again? Show on a block diagram and explain the operation of the addition of 11010. Right? 110 plus 101. Right? So that'll be 1101, right? That's the answer, right? But they want the block diagram. 3-bit, so you will have a half adder, a full adder, and a full adder. Half adder. Right? The half adder will do this for you. right? So that'll be 0, 1 going here, 1, 0 going here, 1, 1. Right? So your answer will be, right? That's the answer there, right? Are you okay with that? That's the block diagram, right? All right. So that was just the warm up. That was just the one, just the warm up, right? All right, next one. One. Right, next one. Let's try this one. Try that. I don't know what have all these screenshot questions. The whole year for like 1994. Oh, you have to do that fast. Do that fast. Done? Right, draw truth table, put in no on the NAND. That should be easy, right? Show how the NAND could be constructed using a quad node chip. So quad node chip basically, they want you to take 4 nodes and make a NAND. Right? Right? So show how a NAND could be constructed from a quad node. Look back at the summary. Look back at the summary and look for 4 nodes that will make a NAND. Yeah, close. Four nodes that'll make a NAND. And then we have to draw a diagram for the next one. Yeah. Oh, yeah, we within this summary, right? Oh, yeah, right? So it knows to create that. So you want to extend that gate from four nodes. It is specified. Okay. Let's check it out, right? Right, draw truth table for the no and the none. That should be easy. The next, they wanted to use a quad node chip, right? So a quad node chip basically has quad node chip looks like this, right? And then all you have to do is to connect it up properly, right? So to create a NAND gate, if you have two NOT gates here, connected here, and a next NOT gate here, connected here. Right? The quad node chip will look like that. Right? You might have it lined up differently, but a quad node chip have them lined up like that, right? Two here, and you connect it up. All right? That's what a quad node chip will look like in real life. Same connection, right? A knot and a knot. A knot and a knot going into no, and then a no connected to a knot. Right? Right, next part. Next part, they said, anybody figure it out? The next part? Huh? Patrick. Let me see. A two-door car has switches on both doors. Right? The switches which are on as logic 1 only when the doors are properly closed are connected via logic gate or warning light. The light comes on if either door is right. The light comes on if either door is not closed, right? So closes are what? Closes are what? Yeah. Draw up a truth table to represent the action and then draw a diagram of the circuit required. So let's see, right? Question said that when the door is closed, it's a 1. Right? Door is open, is a 0. The light comes on if either door is not closed, right? So let's see here. So you have door 1 and you have door 2. No, this is not a flip-flop. That's what it's asking. Right? You have to come up with the circuit. Right? Door 1 and door 2. 1 is closed, right? Remember, 1 is closed and 0 is open. Right. 1 will give you what? In this scenario, 1 is 0, 1 0 is. What about 2 zeros? 2 zeros is up, a 1. What gate is up? Has it? And then gate. And then gate will perform the operation. Oh, you know the NAND gate? Look at the truth table. Look at the truth. Nobody they gave you the info. Question said the door closes at 1, the door opens at 0. And the alarm will go off if one of the doors open. So the alarm going off is here. Door open, door open, door open, door open. That's an example of a control circuit. Right? Right, so in order for you to figure out here, in order for you to figure it out, you need to set up a truth table, right? Take the info and do a truth table. Right? And then from the truth table, you can kind of figure out what gate or gates to use. All right, next one. Draw SR flip-flop, or you can handle that. Right? Try part 2 there. You join the circuit and do the truth table out. Be part 1.
This one's you want.
Which one? Yeah, I go to over here. Right, do B part 2 in the meantime. Right, do B part 2 in the meantime, right? What is that? What is that? Triggered, right? Right, that is triggered by stable, right? So you have to figure out what the trigger. Downward pulse, right? So 1 going to 0. Right, watch here. Right, you have 2 types of flip-flop. There's the NOR, right? So in the NOR flip-flop, let's start over. Once you figure out 1, you figure out 1. For the NOR flip-flop, let's start here. Right? You have no output to help you at all. What we know about NOR gates? A 1 will always give you. So this 1 will always give you. And that's going over part 1 for, right? You're all doing part 2. Right? So do watch it. Watch it. Right? A 1 will give you 0. This is the output that's fed back as input here. 0, 0 into NOR gators. 1. 1 will come back here. 1, 1 still giving you 0. So that's the output, 0, 1. Okay, that? Now we have previous output. So I can change this one to 0. Watch what that will do. 0, 1 into NOR gate will give you 0, 0 will give you 1. It's not changing. So 0, 0, keeping the previous output. That's why it's called saved or latch. But if I change the outputs now to 0, 1, right? A 1 will always give me a 0. 0, 0 will give me a 1. 1, 1 giving me 0. So my output now change to 1, 0. Right? And if I put 0, 0, I'll save it. That's why it's called a flip-flop or RS. R is like when you reset it is this. And S is for save. Save is like 0, 0. It have a 1, 1, but tell me what's the problem. Since you want to know about the 1. 1, 0 giving you 0. 0, 1 giving you 0. What's the problem with 1, 1? And that's disallowed, right? Yeah, pump wouldn't function properly. These two must be opposite. So 1, 1 is disallowed. Yeah, we done? Hurry up. So we had to figure out what will happen there. Right? So we said the trigger is a downward pulse, a 1 going to 0. Right? You don't really have, to be honest, you don't look at the diagram anymore. Right? You can just look at it in truth tables. Right? 4 missing up. Don't know why the 4 not showing up there, but 4 missing. Oh yeah, drawing truth table path. Right? Look at the inputs. When the input goes from 1 to 0, what will happen to the output? It will switch. Right? That's what I'm looking at. Look at the input. Say, look at X is the input for Y. Right? X is the input for Y. So look at where X going from. And that will change Y. When you're done, use Y to figure out. Excuse Andy. Excuse Andy. Andy, finish here. Then the output will change. Huh? No. Watch here. X is the first output. Y is the output from X. And Z is the output from Y. Pardon me here. All right. We're going through the table and see if we figure it out, right? So we're done. Downstairs. Go for the clean and come and tomorrow we'll go downstairs and feed it. I love it. All right, let's see what you're gonna let's pick on Shibara. Right, what's the trigger again? Right, the trigger is 1 going to 0, right? You're seeing 4, right? I can't leave it there, that's the problem. Anyway, I got on the back and right. All right, but hopefully you can see enough there, man. Right. So 0 going to 1, will that cause anything? Will that cause Y to change? No, right? 1 going to 0, will that cause Y to change? 0 going to 1, will that cause Y to change? 1 going to 0, will that cause Y to change? That's okay? Now, Y will help you figure out 0 going to 0, will that cause Y to change? 0 going to 1. No? 1 going to 1. 1 going to 0. Yes? Right? That is the output. Right? Please, whenever you're doing binary, whenever you're doing the theta, you should see a pattern, right? We are now reached by 2.5 hours in the break. That happens. All right, let's go again. Let's just squeeze in one more. Last one. Just the application of it, right? Yeah. Well, get that those part 1 and 2, right? Right? Do a quick little sketch and then I'll leave it on this part here for you. Do a quick little sketch and I'll leave it. And then let's go to AC theory. I'm not doing up arms right now. I can do it in the morning. Right? That comes out there, there's a high chance that will come again. Right? So I'll leave that for last. Everything coming. That one was easier, I don't know why this woman wants to bring madness, not the logic, it's something like this. I think if you get full amount of question, if you get drafted, it has every year, 5 years now, I remember that one. Right. So you have the circuit, right? You must know the circuit, but it's on the board still. Just label it X and Y instead, right? Same circuit, just label X and Y. Right? Do the truth table, please. Complete the truth table and explain what they want. Whatever the diagram, something else I see over here. I haven't noticed a long time. I don't know why. It's like how the diagram is, like you can make diagram parallel series. Like where you do flux it and flux up and it gave us a clue. I just can't remember like you just connect a diagram with parallel. But so it's 2 years ago, 3 years ago. Oh yes, would I make it tonight? Okay, what I. Yeah, you can also that loud. Ready? Ready yet? Miranda? Anybody sign up for electrical engineering at the first? You can't get professional without computer to one alone. Are you one already? They accepted already.
Yeah.
We can get one alone. So when you did one again, that's how the electrical. Huh? Alright, that's
Yeah.
there was not 5% I just want to get the one out. But I'll make it for the day because they have one. That's you.
Yeah.
Last minute. Colore. Ah? Cosa non la guardi? What? Valore? Oh, big view on there. Olha melhor.
Yeah.
So you have last minute and then we start AC theory, right? Huh? Correct me there. That's correct. Then we'll do AC theory. Okay, that's very good. All right. No way without that. So I don't know. All right, let's correct it. Let's correct it, right? Right. To be honest, you didn't want to look at it. That's right. You didn't want to go back and look at the truth table, right? Because you'll recognize what happened, right? 0, 1. Right, 0, 1 giving you 1, 0, 0, 0, saving it, right? When you flip the inputs, it'll become 0, 1. 0, 0 will save it. This will flip it back and this will save it. That's okay? You don't even have to look back at it, you don't have to go and use it, right? Right, by considering, yeah, already. Hello, okay with that? By considering the rule of feedback in the circuit, and the type, what? By considering the rule of feedback in the circuit and the condition for the type of wave to have right, so basically you will have to go through it and explain to them why that happened, right? Same for the, it'll be the same, but instead of 0, 0, say with 1, 1. It'll be a little different. Where you see none? Where you see none? Oh yeah, none that's the opposite. Right. Explain why the output doesn't change, right? So right, so what you will say is when I2 changes to 0, right? When let's go and see it from here. I'll see it from here too. Right, I'll just go back to this and say it, right? Yeah. Right. Yeah, you'll say in words, right? Yes, sir. Everything I do here, you'll say it in words, right? Huh? right? So when the one goes to 0, right? Hey, I'll let you up now. Right? When the one goes to 0, 1 0 in the NOR gate still gives you 0. Right? And then 0 0 in the first NOR gate still gives you 1. So basically the output's not changing. So the outputs are not changing when the I2 goes to 0. That's what I can really say. Right? The output. But just tell it quick. That's like too much. Right? Right? Yeah. Huh? Huh? Right, so when I2 changes to 0, huh? I just want to say the same thing again. When I2 changes to 0, the output Y is still 0. Therefore, the output at X, therefore the output at X will remain at 1. Right? And then that's why nothing changes, right? So first up, X and Y remain the same. All right? X and Y stays the same. All right, next, let's take a look at AC theory. Right? Let's take a look at AC theory. As I said, I'll leave it on upper arm, so now we'll do it in the morning, right? Sometime in the morning. We'll do over upper arms, right? Or I'll just send you a link to the video and what to do. Right? Let's take a look at AC theory, right? Right. So if you had to summarize, if you had to summarize AC theory, what is this? If you had to summarize AC theory, what you would say? Right? AC theory is basically taking an alternating supply and learning to work it as a direct supply. Right? So AC theory basically takes this alternating supply and gives you an average. Right? That's called the RMS. Gives you an average that will work as an equivalent DC. Right? So we had to be able to find IRMS, BRMS, PRMS, and so on, right? And the next thing we had to be able to do is to take an alternating circuit and convert it into a direct circuit, right? Not circuit, sorry, right? How are you doing that? Half wave rectification followed by full wave rectification followed by smoothing. Are you okay with that? That's basically AC theory. All right. So let's take a look at it here, right? Right. So, right here is your AC theory. Right. When they say peak to peak, you have to remember peak to peak is your highest to your lowest, right? So for example, in this case, the peak to peak value is 4. 2 minus minus 2. Right? If they give you peak to peak value to figure out your amplitude, you have to divide it by 2, right? Don't forget that, yeah? Peak to peak is peak. So peak. Right? So peak to peak value is 2 minus minus 2, which is 4. All right. So from your peak to peak value, in order to get your amplitude, you have to divide that by 2. All right. Right. 0 to peak, well, 0 to peak is the amplitude, right? Root mean square is the average of the alternating supply. Root mean square is that green line, right? How do you find root mean square? Everything right here. Well, of course, hopefully you remember what is frequency and thing, right? Right? You have VRMS, you have IRMS, right? That's how you find your root mean square, right? That's the average value. If you have to do any calculations, you need this value. So you take a peak value, and divide it by root 2. Right? So that's your VRMS, your IRMS, and this is how you find power, RMS, right? That's your average power being delivered. IRMS by VRMS. Right? Quickly, the RMS value of an AC is equivalent to the value of the DC, which will dissipate power the same rate. Right? You have your diode, so you have to be able to read up on your diode, P-type, N-type, and you have to explain how power and reverse biases work, right? In a P-type, the charge carriers is what? In a P-type, what are the charge carriers? Holes or electrons? Holes, right? A hole is when an electron leaves, it will leave a positive charge, right? And N-type, the charge carriers are electrons. So, whenever you connect a diode could either be powered bias or reverse bias, right? When a diode is powered bias, right, the depletion region is really small. So it's really easy for the electrons to move across from the N-type to the P-type. Do the P-type really move? No. When the electrons move, they will leave a P-type. So it looks like a P-type moving. But really and truly, it's the electrons moving. So if you look at that diagram there, that diagram is fault bias, right? Because the depletion region, you'll see depletion region, the depletion region is really small, right? So that's forward bias. So the voltage to cross that depletion region, depletion means nobody there, nothing there. So you're trying to cross a desert, right? And if you have enough water, you can cross it. But if the desert is too large, you can't cross it. When that happens, that's reverse bias. All right? So you have to be able to draw and explain what happened during forward bias and reverse bias. Okay with that? So because the depletion region builds up so large, the electrons can't move across, right? Right here, we have an example of half-wave rectification. Right? So okay with that? Is there any way to smoothen that? Can I smoothen a half wave? Yeah? No, the Wheatstone bridge is a full wave and then smoothen it, right? But if I want, I can just smoothen that right there. Connect a big capacitor and I can smoothen it right here. But the capacitor has more work to do. So it wouldn't be as efficient. Right? So ideally, we have to do full wave rectification. And this here is your circuit for full wave rectification. Right? So that's your bridge here, right? Right? That's a bridge circuit. And this is full wave. You would recognize in full wave, right? You would recognize in full wave now that the gap between smoothing is smaller. Right? So I don't need a big capacitor, so it'll be a little more efficient. All right? So I want to show you how full wave does work, right? Look at the circuit there. All we need to make sure is that when we draw our circuit, current flowing this direction all the time. Once that happening, it's full wave rectified. How you draw the bridge? Really easy. You have two diodes in the same direction and those two in the same direction. Always make sure that on opposite sides, they are parallel, they're in the same direction, right? And then these two, make sure that current can go down there. So let me show you what happened here. So you have an alternating supply. Right now, I am assuming here is positive and here is negative. So current going this way. When the current reaches at A, where will it go? To B or to D? It can't go to D, right? Because it reverse bias. So it cannot flow here. It'll flow up here. Everybody okay with that? When it reaches at B, will it go to C or will it go to the resistor? So it will go this way because the resistor is reverse bias. So it will come down here. Huh? What? What's it? Oh, sorry. How many diode reverse bias, right? It means how many diode reverse bias. So nothing flowing there, right? And the current going through the load, so we'll be good to go on that cycle. When it reaches here, though, where will it go? Why it would go up to A? Right. Current goes from a high potential to low, right? So here is high and here is low. Remember, here was already high, so I don't know where you come on from, right? So it will not go to C because C is a higher potential. It will go from D to, sorry, it can go to A, it will go to C, and it will follow that path there. That's okay? So it follows the path in red. Yeah? No, C is a lower potential. Because A, remember, current just come from there. So that current there has a higher potential than the current at C. C have nothing, right? C have nothing basically. So C has a low potential. So it will not go back to A, it will go to C. And then let's just say here is positive and here is negative now. Remember, it's full wave rectification, right? So it will go here, it will not flow there, come here, and it will flow through the resistor in the same direction. Okay with that? It will come back here. When it reaches here, it cannot go to C, it will go back to A, and then come down here. That's okay? It will not go to P because P is a higher potential than P. All right? So that's the circuit for full wave rectification. Right? Full wave means the entire wave is rectified. But now we are to smoothen it out. Right? Adding a capacitor. That capacitor will smoothen it out. Here's what smoothing is. Smoothing real easy. When the capacitor is charged, it will begin to discharge here. It will charge up again. Discharge, charge up, discharge, charge up, discharge. And the larger the capacitor, the smoother that will be. All okay with that? So the bigger this capacitor, the smoother it will be. All okay with that? Right? So that's the way, that is the theory. Make sure you know about input transducers. Basically, input transducer is a device that will take an input and give you an output. For example, LDR. LDR will take in light intensity and give you a resistance. Right? Those are input, output. It's like a speaker. A speaker will give you take electrical and give you something else, right? So you have to know them. Right? And we have to know about thermistors, how they behave, LDRs, how they behave. That's the symbol by LDR, right? Sometimes in a module 2, as you saw before, sometimes in a module 2, they could give you a full resistance question. So we have to know resistance in order to do questions as well. If you look at last year or year before, they brought a Wheatstone bridge in a module 2. And they were able to do that because LDRs and things is very funny. That transducer, that's in module 2. But they put it onto a circuit as a module 1. So you had to know your resistance and thing as well, right? So we'll go over that. Right? Anyway, here, look at that circuit. That circuit is a what? It's called a circuit. A potential divider. Right? That's a potential divider. So it will take your entire supply and divide it. What's the entire supply there? How much volts? 5. Right? And the potential divider is this. Your V output is your total supply by your R1 over your R1 plus R2. Anybody remember what R1? Look at the circuit. R1 is what? R1 is the 47 or the LDR. R1 is always here, right? Where you connect the output to the cross, right? That is your R1 and that is your R2. Right? Please remember you have two types of LDR. You have negative coefficient and positive. Yours are generally negative, which means that the higher the resistance, the lower the intensity, or the higher the intensity, the lower the resistance. All that means in the day, when you have plenty light intensity, the resistance very low. Right? In the night, when you have less light intensity, the resistance high. Okay? That's all that means. Negative coefficients mean inversely related. Right, and then we'll get pop amps after that, right? We're not doing that right now. Let's do a small thing here. Where did I put that? Right? That's not what I don't see. I'll put it out that way. Alright, while I look into it, just try this one here. This is 2005 if you have it. Start there. Number 4. 4 part 3. We have no idea about part, right? What's here? Huh? Yeah, part 2 we starting from. Starting from part 2. Oh wait, that's the same here. It's number 5 and now you have to one other. Anybody have a PDF for that? 2005? 2005, what happened? 2005, I think it's paper 1. 2005 is paper 1. Number 4 and number 5 we do it. Yeah, sorry. Right. What's the general equation here? V is equal to V naught sine. Alright, well, you want to get frequencies, but you can put 2 pi ft, right? Same thing, right? Remember, omega is equal to 2 pi f. right? So the frequency is how much? 50 hertz, right? 50 hertz. Let's go again. How? So, how compare this here? Right? 2 pi f is equal to 100 pi. Right? So you're comparing this value here with this value here. Right? And then subtract. Right? And the pi will cancel. The pi will cancel and you get f is equal to 50. Okay? Very good. Andy, very good. Next part, on the axis below, catch both of them, 2 complete cycles. What? Oh, what be out? On the axis below, sketch both the input and the output for 2 complete cycles indicated. Right, but what be out? Oh, this is BN. Oh, sorry. It's applied to comparator. Remember the comparator? Yeah, applying that to the comparator. Remember comparators? So probably here's what they want, right? I'll just go it over fast. Right? Yeah, you will have to give them exact values, right? Right? You'll have to give them exact values. That's your BN graph. But remember, a comparator does what? I'll go over that later. But a comparator what? Compares, right? So most likely one was the alternating and one was a direct value. Anybody have the actual question? But here is what the comparator connected to what? Alternating supply and goods. Goods, right. And then you have to compare the values, right? Which one is connected to? We're connected to which terminal? Right? It is connected to the positive. So you're given and compare, right? So whenever this value is more than this value, it will saturate low. Whenever this is more than this, it will saturate high and low. Remember that? Yes? So it's alternating to direct. Anyway, I'll go over that later on in the morning, right? I'll go over that in the morning. Right? Sketch the graph for diode. What does the graph for diode look like? What does the IV graph? What does the IV graph for diode look like? Right? Something like that. That's okay? Something like that, right? It's a little sharp. It's a little sharp, but drop on the negative side. Right? This is the part I was looking for, right? Catch your tree graphs, please. Catch your tree graphs that you might detect there. Catch your graph for each one, right? You're done. Catch each one, right? Finish already? Yeah, food. All right, so the first one is what? Right, the first one is half wave. What happens in the second one? Kind of like smoothness, but not perfectly smooth. Right, something like that, right? Right, next one is what? Next one is full wave, right? Yeah, yeah. If we can just draw the right, well, I mean like that there. As I mean. Yeah. So draw this here. Yeah. No, but remember, this wouldn't happen. So that wouldn't happen. Right? So you can't include that during that because watch this here, right? During this part here, the capacitor will charge up, right? When the voltage starts to drop, the capacitor will start to discharge. So it will discharge, and then when it reaches this particular value here, right? When the potential is a little bit higher, it will start back to charge again, and then repeat the cycle again. So there is nothing underneath here, nothing underneath there. All right. And the next one is full wave, right? Next one is full wave. Last one part. Same here, right? Same here, number 7. Right, the part that's missing is transformers, right? Sometimes this becomes a transformer question. I want to try it one time. Actually, let's try the whole thing one time. Well, you have 5 minutes, you have to move fast. In exams, this scenario could happen. You have 5 minutes and you have a whole question to do. What are you going to leave it out? Huh? Just give it extra time, huh? All right, let's go. Let's try the first part. We can talk it out. It's not that difficult. State the relationship between peak value and RMS. What's the answer? VRMS equal to the peak value over root 2, right? Type part 2, that calculation there. Yeah. Type part 2. Type part 2 there. Right? Part 1 was VRMS is equal to peak value on root 2. Try next part there, Shabara. Or you want it until you want it already. Ready? Try that in. Calculate the direct current that will produce the same quantity of thermal energy in a particular resistor as an alternating that has a maximum 2.6. What they have to put in? That's here. What they have to put in? What they have to put? Huh? Figure that. I just have mark there or something. I'll do mark. Figure that. Wait, what they have to put here? IRMS. And IRMS is what? Peak value on root 2, right? So that's 2.6 on root 2. All right, right, for ideal transformer, what's the formula again for ideal transformer? NP over NS is equal to VP on VS, which is equal to IS on IP. Right? Got to remember that formula, right? I think that's sorry. I think that right? That's the formula for that is the formula there. What's a month? They'll give it up for the bus. Okay. IP on IS is equal to VP on VS plus IS on IP. Right? That is only if the transformer is ideal, right? What does ideal mean again? Which means that the input is equal to the output, right? Input equal to the output. No, you have to explain how it works. I just give you the general formula. Right, so they gave you a transformer. Why they keep giving it RMS values per transformer? Because in a transformer, the alternating current that is used in the EMF, right? Okay, remember Faraday's law? Anyway, we'll look at that in a little while, right? But in a transformer, transformers don't use DC. Transformer use alternating supplies, right? So all your values will be RMS. So a transformer operates at 8.5 kilovolts on the primary and supplies electrical to the nearby at 120. How you find it? NP on NS. Very well. How are you doing that? NP and NS is what? Sorry? Sorry, I missed that. VP on?
Yes.
So what is VP here? What is VP? 8.5? Right. Number one thing when you read your paper, write down, pay attention to your units, right? You'll recognize in the graph questions and all those questions that try and mix you up with the units, right? Right? So a common mistake here is that we write 8.5 instead of 8.5 kilo, right? That's okay? So it's 8.5 to 120. But because of your knowledge of a transformer, you should have known that these transformers are step down. All right? So you might have recognized that value wrong, right? Right? The average rate of energy consumption in the houses is 78 kilowatts. Find the peak value current in both windings. What are they asking for? What are they asking for in part 2? They want the peak value of current. So that's what? Right? In which one? No, peak value. That's not RMS. That's IP, right? So they want the IP value in the primary and the IP value in the secondary. But for us to get the IP, we need IRMS. Okay? How we getting now? Think about it. Look at the value they give us. What is this here? That's power, right? And power input equals to power. But you find P again, P RMS is equal to what? I RMS multiplied by. Do we know VRMS for primary and secondary? Yes, we do. So can we find IRMS? Right? So we can find the primary and secondary. Go ahead, have fun. Do part 2 there first. Do part 2 and part 3. Right? So they want peak value. I just show you how to get RMS. You have to find peak value. Try that fast and then we'll take a break after that for 5 minutes. Oh yeah, find IRMS in the primary, find IRMS in the secondary, and then find peak value. Right? You have to pay attention to what they ask, right? They have to peak value, so they want IP. What the power in secondary? What's the power in the secondary? And then what is the power in the primary? What's the power in primary? What does ID mean again? Okay. So you have to say power, right? Work it out fast, find the IP value. So call on it, choose. That's what I might do. Oh yeah, that's it. Yeah, that's true. Right, what we got? What did you get? So PRMS would have been IRMS on, right? So IRMS are doing the primary first, right? That will be 78,000 divided by primary is 8,500. Right? So that will give you IRMS. How much is that? Huh? 9.18 amperes. But they want the peak value, right? They want the peak value, right? So that will be IRMS by root 2. That's okay? How much you got there? $12.98. Right? That's the primary, right? And then do the same thing in the secondary. And you will end up with what? Current in the peak value is what? Same thing in the secondary. And you'll get peak value. Sorry? 919. So big? 0.24. How's the RMS value again? 650. Yeah. Right, and how you getting the load? How you getting the load? R is equal to voltage in the secondary over current in the secondary. And you get your projected load, right? On the short, 9.19. Yeah. 919 I mean. How about you? What you got? What you got? First one? 12.9, you get a 2 again, right? All right, take a little break, 1 hour. 1 hour, and then we start with module. Next module. Right, take a little break for an hour, right? Right, let's start back. We will do capacitance and electricity and magnets, right? Right, so this capacitance is one of the things that you can see in your module one, right? Right, ready? Right, let's go. So want to talk about capacitors, right? That is basically talking about capacitors and its ability to store charge, right? And its ability to store charge. So if I have to define capacitors at the see there, the charge stored per unit potential, right? SI unit farads, generally capacitance very small, right? So your capacitance is generally in microfarad or millifarad range, right? Right, capacitors are device used to store electric charge. Capacitors consist of two conductive plates, a pair of conductive plates, and an insulator in the middle. The insulator is generally dielectric, right? Right, we know the find capacitance here. If we consider it dielectric, the capacitance of a parallel plate capacitor is given by C epsilon A on T. All right, so you have two little versions there on how to find capacitance, Q1B, and you also have capacitance based on the properties, right? A is the cross-sectional area of the plates, E is the permittivity, and D is the separation of the plates. Here we have a diagram that we use to explain charging and discharging, right? So the way is connected here, right? Will the capacitor be charging or discharging? Charging, right? Anybody remember how to explain it? Yeah, that's here, yeah. Go ahead now. Right, we need to remember how to explain. Right. Right, when it connected circuit, right, nice. When it connected circuit, yeah.
Do you have any comments?
Paul, yeah.
Yeah.
They have something probably like. But not now. They don't. Right. How does it work? So when we connect it, what is B at the maximum? Remember, we have 3 quantities to look at: current, charge, and voltage. When we connect the circuit to charge, what is at the maximum? Current, voltage, and charge. Current is the maximum, right? Charge at 0 and voltage at 0. Remember, the voltage across here, right? So, but when I connect the circuit, the first thing that will happen is that electrons will flow. As the electrons flow to plate A, all the electrons build up there. So it will push electrons away in plate B, causing it to flow to the opposite side. Right? As a result, there's a buildup of potential across the capacitor. Right? This will continue to happen until the voltage across the capacitor is equal to the voltage across the battery. When that happens, and they're both equal, the capacitor is fully charged. All right. So current starts at maximum. Current starts at maximum and decreases because as time goes along, less and less electrons flow in its circuit, right? As this potential here increases, less electrons will be able to leave from here to here. All right. So therefore, your current graph will behave like this. Your voltage graph will behave like this, and the charge graph will behave like that. And you have to know the equations for each one. When you take the switch and the connectors here, what is maximum? What is maximum? Current maximum, voltage maximum, and charge maximum. So they will behave like that. All of them behave the same way while discharging. Right? And the explanation is simple. As soon as they connect the circuit, electrons will leave. Right? As electrons leave the circuit, the current value will drop, the voltage value will drop, and of course, the charge value will drop. Right? And besides knowing how to explain it, everything there, you have to know the graphs for charging and discharging for voltage. There are your formulas. Right? You have to know the formulas for charging and discharging. For current, voltage, oh wait. Shucks. Yeah, that's missing. All right, I'll just draw it here for you. Yeah, that's missing. Yeah. Right, so we said charge versus time will look like this, and the formula is identical to this. Charge is equal to Q naught by 1 minus E minus T on RC. That's the charge, and current will look like this. I versus T. I is equal to I naught E to the minus T on RC. Right, on the next side, you have voltage. So charge will look exactly like that, and current will look exactly like that. Right, and they all have the same looking formula. Q is equal to Q naught E to the minus T on RC. I is equal to I naught E minus T on RC. Right, so those are your graphs. You have to be able to draw and explain your graphs for charging and discharging. The only thing you really have to remember is that when you're charging, current is the maximum. Right, the current kind of behaves different. Right, you have to learn your formulas. Q naught is your what? Q naught is your amplitude or your maximum charge, right? What is T? T is time, and RC is your what? Time constant. Anybody remember the definition of time constant? What's the definition? And the it's a constant, right? Of time. 1 on E of the maximum charge. Time it takes, right? Time it takes to reach the 1 on E of the maximum value. Right? Time it takes to reach 1 on E of the maximum value. Remember, if they gave you a proof, right? They asked you to prove something given some equation or something that you never saw before. Remember what you could also do, right? Take the proof and work backwards. And it will kind of give you an idea where to start. Are you okay with that? Are you okay with the graphs and equation? Right, so please remember, the formulas allow you to find any current at any point in time. By the way, capital R is what? Capital R is the resistance of the circuit, and capital C is the capacitance, right? Okay, so that's the capacitors. What's the next thing that we need to know about capacitors? Right? We need to know when they connect them in series, how they behave, and in parallel, how they behave, right? How they behave here in series. Capacitors in series behave the same as in parallel, right? And capacitors. Got already? Sorry, a little. Right? Capacitance, no, yeah, I feel it. Capacitance in parallel is the same as what? Resistance, right? And can you prove it? Go ahead, have fun, prove it. Just ask me, just randomly, I will start you up here. Do the proof for 3 capacitors in series. What's the starting line again? The starting line is what? V is equal to, before you use V is equal to IR, or Q is equal to IT, there's something important we have to start with. What splits up in series? Voltage splits up in series, right? So V is equal to V1 plus V2 plus V3. And now you're using C is equal to Q1. Let's see if we can get it. Try and see if we can find capacitance in series. Find V, V1, V2, V3, and work it out. That's for 3 seconds. Three seconds to go. Watch this, right? Okay. Right, so we know that voltage is equal to charge over capacitance, right? Charge is the same in series or splits up. Charge behaves same current, right? So Q over C is equal to Q over C1 plus Q over, and then what to do? What are you doing after that? Huh? Yeah, or you can just divide everything by Q. Right? Divide everything by Q and you'll get 1 on C as 1 on C1, 1 on C2 plus 1 on C2. All right? So those are the things that we need to know for capacitance. Oh wait, yeah, one last thing. One last thing. Right, one last thing we need to remember is energy stored in a charging capacitor. If I give you a charge versus voltage graph, charge versus voltage graph, the area under the graph will be your energy stored. Okay, so if I ask you to find at any point in time energy stored, you can use any one of these. Half Q by V or any of these, right? Going home, right? Oh, sweet old. That's like. Hey, it's much older, not yet. I realize. Huh? Did I get oh no, it's something like it's I like something. So I just didn't like food. What do you like? Nobody. Oh, okay, so do the things that we need to know about the capacitors. Yeah, let's try one, right? Let's try one here. Of course, we could actually graph something, right? But right, take a look at it. You know how to ask you one like this, right? Take a look at that graph there. Right? Take a look at the graph that they gave you. Look at the graph they gave you, right? What did they do with that graph? What they did with that graph? What you do? They linearize it, right? They took ln on both sides. So have fun. Linearize and tell me what the gradient is, please. It's not much people well. I don't know. Linearize that for me, please. Basic advanced stuff. Basic stuff. Linearize that, please. Right, what is here? For those who don't remember, not much people, let's take a look at it. Right, let's see how something like this, right? Y is equal to AB to the power of X. Right? And I want you to linearize it. What you do is take ln on both sides. Ln Y is equal to ln AB to the X. This is multiplied. So we can create it up. Ln Y is equal to ln A plus ln B to the X. One common mistake is that people forget that X is over the P alone, right? Right? The X is not over A and B, so you can't bring the X in front here as the X. The X is only over the P alone. Right? When you're done there, you'll get ln Y. You'll get ln Y X ln B plus ln E. So after linearizing, this is my y-axis, this is my x, this is my gradient, this is my y-intercept. That's okay? That's generally how you linearize something of that form. So copy down what you need and let's go back to the last one and see if we can do the same thing. Yeah, this is right. Try that here, please. Linearize this and tell me what the gradient and then well how to find anything else. Done? Ready done? EXP just B. It's B. Right, so you should have ln right, so you have V is equal to V naught E to the minus T over RC in Q, right? So when you take ln, you'll get ln V is equal to ln V naught E to the minus TRC. That can be broken up as ln V is equal to ln V naught plus ln E to the minus TRC, which is ln V. We all know that ln E is 1, so you can bring down the minus 1 on RC by T plus ln V naught. Right, so I just bring that down, right? And I separate it out. Ln E is 1 here. Right, bring it up, and you will end up with 1 on RC. That'll be a gradient. This is your y-intercept, this is your x, and this is your, sorry, that's your y, and ln V naught is your y-intercept. That's okay? Please remember, don't break your axis if you need a y-intercept, right? Otherwise, you'll have to use the formula to find the y-intercept. Okay with that? Right? So when you linearize, it'll look like that. What do you guys say? Right, to finish off this here, please. Calculate the gradient in case you can see. Pick 2 points real fast there. And all you please, when you're reading your values, so look for your units on your y, look for your units on your x, right? Right, don't just write, if you see in 2.4, don't just write 2.4, right, Andy? So you're not writing that. That's más que zoom in there. Right, just use the value on the y on the one down there. Right, this value here is what? 2 points. 2.1. 2.4, right? Sorry, 2.2, 2.2. 2.2, right? Right, so the first value is 0, 2.2. And you can pick one down here if you want. That value is 50. 50 what? 15 minus 0.2. 15 minus 0.3, yes. Find the gradient. Minus 0.3, yeah. 0.1, 0.2, 0.3. Find the gradient and then go ahead and see what it was after. So I see just find the gradient. Try that there. Right? What's the gradient again? 1 on RC. What's the gradient? 1 on RC, right? But you all got three gradients. Minus 1 on, alright, the gradient is minus 1 on RC, right? And we just get up 1 on 20. No? What you got made up? We don't dig into work it out. What you got? Same thing, right? Yeah. Right, then go right ahead and find the time constant. Time constant is what? RC, right? Then they give us an R value. They give us an R, and we know R. Oh Lord, did I use it for the questions? Anyway, we can talk it out. Right? How we getting the so how we getting time constant? Time constant is always what? R by C. So R by C is 20. Then they want us to find C. How we getting C? Right? T divided by R, right? And well, I'm missing up on the question. I do have R. Right? R is a thousand, nothing. Or 1 mega ohm or something. I can't remember. Right? Anyway, but T on R. How we getting EMF? What's the EMF? Andy, what's the EMF? I do it thinking of it. I do it. Anybody? How we getting EMF from this graph? Huh? Anybody? Anybody write an example? Oh, what? Area under the graph will not give it that product. Right? What was the y step again? I don't know what it represents. ln V naught, right? And V naught is the what? That's your max voltage, right? And your max voltage is same as the EMF. Remember that? Show it the circuit. Your max EMF is the same as your, so your max V naught is the same as the EMF. Okay? So you have to find your y intercept and work it out, right? Find the EMF there. I think the R value was 1 mega, right? What you all got? What you all got? The EMF. Right, the value here is what? 2.2, right? So therefore, ln V naught is equal to 2.2. So V naught is e to the power of 2.2. Yeah. What's that? About 9, right? Next one. Around 9, right? Next one here. Gosh, that's how it works. Or as a multiple choice, try that fast. You can do that mentally. What you all think? A, B, C, or D? Dog? Yeah, dog correct. Right, the resistance wrong because in parallel add them up. The charges are not the same, the energy not the same because the charge is not the same. But the potential difference is the same across them because they're parallel, right? Try this pass here. Remember this, we did it once, I think. 5. And I'll give you an next one. All right, have plenty more. Have plenty more. I'll give you one I didn't do as this. There is one in right 2008 we were rest of the region. But they have that? Oh wait, no, not worry. You gotta plot the graph. Right, when you plot no graph. Try to see do part A first. Right, do part A, let's take a look at part B after. I'll go back into part B just now, right? Come now. Let's get handle part A. Yeah. Let's keep all that. Alright, yeah, let's do it now. Do part A first. right? Above 110, the capacitor then discharges completely in 3 time constants. So what does 3 time constant give you? What is that? 3 time constant is what? All right, I'll come back to that part. So let's take a look at A. The time between flashes. That is, and it tell you what it is, right? The time it takes for the uncharged capacitor to reach a value of 110. Right? So the one time between flashes is the time it takes for the capacitor to reach 110. So it means that the capacitor was what? Uncharged, right? So it was at 0, right? So the formula that we're using here should be one that they gave you. The one that they gave you, V is equal to V naught by 1 minus E to the minus T R C. Right? What's the value trying to reach? 110. What's the P naught? 120. What are we trying to find again? P. R is what? 1 by? And C is what? 1 by 10 to the 1 by 10 to the minus 6, sorry. You can help me now? Find for T. Find for T. Right, so we said that the V value is 110, the V naught value is 120. Right? We're trying to find T. We said that R is 1 by 10 to the 6. And we said that C is 1 by 10 to the minus 6. So that will cancel off nicely, right? So that'll become 1. So 110 on 120 is equal to 1 minus ET on 1. So you can leave out that, right? We're trying to make T the subject. So let's just switch it around here. E to the minus T is equal to 1 minus 110 on 120. Okay. And then you want to make T the subject. So you'll get minus T carried across ln of this value here. Right? And that will help you get T. What's that? What's ln of 10 on 120? Huh? 2.48. So I can make sure. 2.48. I was metal, 10 to the section. 2.48, right? But the minus will cancel off, right? The minus will cancel off. So it's 2.48. That's okay? So the time is 2.48. Right, but what about the next part now? The duration of each flash. How long will a flash take based on the information? How long will a flash take? The capacitor discharges completely in 3 time constants, right? So that'll give you an idea how long a flash is. Okay? So a flash is what? Because remember the lamp will stay on until it discharges, right? So the lamp will stay on during that period. So the duration of a flash, right? Duration of a flash is 3 time constants. Right? Find a time constant, work it out. Yes? See why? Right? So the question said that the capacitor discharges completely, right? During that period there. Right? And time constant is what? R by C, right? And we have R and C already. The time constant is R by C. So that's 3 seconds. And next part. I won. 1 by 3 is 3. This is R by C here. And last part, find the energy released in a flash. I find energy. Right, so half CB squared. C is how much? 1 by 10 to the minus 6, and V is what? 110 or 120? 110, right? Because it reached 110, right? Right, during a flash, the voltage reaches 110. Okay? How much is that? 6 point? Minus 3. Right, so now we did this already, right? But I just want to just look through this here. Right, so here we did this already, 2021, right? Right, so here we have what? Here we have a capacitor, right? And they have it discharging, right? Yeah, we can go and do, I just want to run through this one, right? Right, so you have it discharging and you want to plot the graph. How it will look? What's the shape of the graph? Right, it's discharging, right? The time constant for each type of discharge can be defined, and they give it a definition. Use the definition and the graph to find the time constant. What we did again? What we did? No, we didn't linearize it. They want to use the graph to find the time constant. So the time constant is what? The time taken to reach, well, it's RC, but from that graph, remember the graph looked like this, right? Remember the graph looked like that, right? How are we going to get from the graph? Find 1 on E of the original value. Find 1 on E of the original value and read of the time. That's okay? Find 1 on E of the original value and read of the time. Okay, and then use the value to find the capacitor. How are you doing that? That's where you use tau is equal to RC, right? Well, I will call it simple. T. Time constant equal to. So that's the definition for time constant. Time taken to reach 1 on E of the original value. Right? And then you use that and you find out value, right? All right. That's one of the point out that to make sure you remember those little things, right? Remember, if they give you like constant for the dielectric and thing, the formula to use to find capacitance, right? Define charge. And a little bit of potential gradient. All right, forget that one. All right, so I don't want to point out that little thing to you. All right, next thing we had to quickly look at. Let's look at electricity. Right, so here we have some basic definitions that we should remember. Right, those definitions, they are for right current and voltage and all those little things, right? But what's the difference between potential difference and EMF again? Same unit and everything, but what's different between potential difference? What's the difference between potential difference and EMF? Or something a little better than that. So remember, EMF is from the supply, right? So EMF is what? EMF is the electrical energy converted to what? So other forms of electrical. So think about it and then you go again. So EMF and PD. Right, so remember the load. The load is where you have PD, right? And the load takes the electrical and converts to other forms. Right? So terminal PD of PD is electrical to other form. EMF is the other way around. EMF is other forms to electrical. That's okay? EMF in other forms to electrical, and terminal is electrical to other forms. All right, I think I have it somewhere in here. I thought I had it somewhere there. Right here, look at here. Right, PD is electrical energy to other forms. EMF is other forms to electrical energy per unit charge. Right? The relationship between that's the definition for each one of them. Right? Electrical energy to other forms per unit charge. That's the definition PD. Right? Other forms to electrical per unit charge. That's the definition EMF. How are these three related again? How are these three here related? Internal, terminal, PD, and EMF. EMF equals to the terminal PD plus I by small r, right? Right, so you have those relationships. Please remember, if they ask you to prove it, you start with the conservation of energy, right? Energy supplied by the source per unit charge equal to the energy used by the external circuit per unit charge plus the energy dissipated by the internal resistance per unit charge. Right? That's the conservation of energy. In case they ask for resistivity, resistivity is resistance, area all over length. These are all the formulae you have to remember. Right? To be honest, you only have to learn this one. You should know this. Right? And you can work out all the others. Once you learn this and you remember this, you can work out all these. So the most important one here is W is Q by V, and then power is work done on time. Once you remember those two, you can work out all the others. Right? You can work out all the others from right there. Q is equal to IT, plug in Q. V is IR, plug in V. And I is that. Plug in W. W is Q and V, and you'll get this, and then you'll get this power. This one here, power loss, right? Don't forget that, right? So once you remember the top two, you should be able to work out all the others. Right? Drift velocity. What is drift velocity again? Right, that's the formula, but a small definition. It's the average velocity of all the electrons when a current is applied to a conductor, right? And drift velocity is I is equal to NEAV. Okay? If you had to find drift velocity, VD is equal to I over NEV. That's okay? That's the drift velocity, that's the average velocity of all the electrons there. Right? You have to prove it. Most important thing is you have to remember N. N is what? Number of charge per unit volume, right? Call it charge density. Right? That's the charge density. Right? So you kind of have these steps here. Here. You have these steps here. Q. Q is the charge. That's the charge density multiplied by the charge of an electron multiplied by the volume. Right? So to find Q, Q is equal to the charge, which is the charge density, multiplied by charge of an electron multiplied by its volume. Volume is equal to area by diameter here. Right? And once you have that, we know that I is equal to Q on T. Right? They show you how to find T, and when you divide it, you'll get I. And you can make V the subject of the formula right there. Most important thing is you have to remember N is the charge density. N is the charge density, right? N is the charge per unit volume. Okay? Once you remember charge density, you should be able to work out everything there. Right after that, we have your graphs for you have your IV graphs, filament lamp, diode, thermistor, and so on, right? Next, we have to remember Kirchhoff's law, right? Or what's the principle behind Kirchhoff's law again? Right? Current entering, current leaving, right? At any junction, current entering is equal to current leaving. That's okay? How do you apply Kirchhoff's second law? The sum of the EMF is equal to the sum of I by R. Remember loop analysis, right? Once the loop going in the same direction, current will naturally flow positive, right? If it's going against, negative. To help me out here, let's take this small example here, right? Let's pretend current flowing. Let's pretend the current flowing here. On top here is I1. All here is I1. Here is I2. Here is let's make up some values. Here is 10 volts. Here is 20 volts. That's 8 ohms, 10 ohms, 5 ohms. And let's choose a loop going in this direction. All right? Right? You know how long I muted? What is that? Oh. All right, sorry there. Can I ask me this for a long while? All right. All right. Right, help out here. Would it 10 volt be positive or negative? Sure. Right. What direction current flow in? Current will flow on the from plus to minus, right? So if the loop going this way, current will naturally flow that way, right? That's okay. So therefore, that'll be minus 10. Right? So remember this, right? Remember, if you have a loop, so your loop going this way, and your battery is like this, current will come out of the battery here, right? Well, in a conventional way, right? Current will naturally come out from the plus and go to the minus, right? So therefore, if your loop direction is the same as the direction current flowing in here, positive. But, right, but if it looks like this, current will go this way, and so in a case like this, EMF is negative. Right? Right? If your loop going this way and your I value also going that way, I by R positive. I by R positive. If your loop going this way, but the current going this way, I by R negative. That's okay? So yeah, remember that, right? So let's see if we can apply that here now. Right, let's see if we can apply that here. Yeah. Huh? So long, no. Oh, it's a centigrade. Oh, it's going. Yeah, but I'm not paying anyway. Alright. So what's here, right? So if you look here, let's see if we can actually you do it. Or do this one. Do this one, all right. Right. So apply Kirchhoff's first law. Any current entering? Any current entering here? Right. So therefore I1 plus I2 plus I3 is 0, right? All even, right? Let's focus on loop 1. Right? Let's focus on loop 1. Positive or negative? Positive or negative? That's okay? Everybody okay with that? Right? So it going this way, just like what I showed you here. So that's negative. And it going this way, just like this one. So it will be positive. That's okay? Are you okay with that? Well, next one, you figure out that part. Next is I by R. So let's see. Loop in the same direction, I1. So that's positive. So it's I1 by 4. Same direction. I1 flowing here and here, right? So it's I1 by 5. So I can add up that one time, right? 9. This loop going against I2. So that'll be minus 3 I2. That's okay? That's loop 1. Loop 2 now. Loop 2, positive or negative? Positive or negative here? Positive or negative here? Negative. Watch it good. The loop going this way. Talking about yet. This one here, current will go that way, so that's positive. Current will go this way, so you're going against. Right? So positive 12 minus 4. I3, this I3, right? I3 going this way, right? So it's going against the loop. Right? So it's going against the loop. So that'll be minus 2I3 minus 2I3 minus, no, I3. So that's minus and minus 2, so that's minus 4, right? And then the loop going with I2, so that's 3I2. Huh? What is doing every here? Right? Make I1 the subject, or anyone you want. Make something the subject and plug it in both of them and solve. Right? So let's say you want to make I1 the subject, plug it in here, and then solve these two simultaneously. Don't matter. If you plug in I1 in here, you have I2 and I3, and they both will have the same thing. Right? Just substitute for them in both equations. That's okay? That is your Kirchhoff law. Right? If I ask you to find we'll do one like that. Right, let's try one of practice. Oh, well, the last thing is we gotta remember what potential divider is and how it works, right? That's okay? A potential divider and how it works. Let's try Kirchhoff law there. Go ahead, have one. That's all I give you. I don't know with the values, just find IL, IB, and IC. Right? Just for consistency, so we end up with the same equations. Let's pick the same loops, right? One loop here and one loop underneath here. Right? Let's pick the same loops, right? Loop one on top, loop two. Just practice loop one, eh? Try and get it right. Loop one and loop two, find for I, L, I, B, and I. I just get it signed right and prove it. Finish? I think you're done. What you got? Yeah. I look at those now. Yeah. Ready? Right, I'll do this on the board. Let me show you get the same values, right? I think it was a decimal, small value. Bottle. Oh, we got. Right, let's see if we get. Let's see what values we got here. All right, so this here is the circuit. Current entering at IC, current leaving at IL plus IB. Right? Second law, I choose it clockwise here and I choose it clockwise here. Right? So I'm going with loop one. Right? Loop one. I go in here, I go in any direction, current will flow, so that's positive 12. Any other EMF? No. I go in against IB, so that's minus 0.1, 0.011 IB. I go in with IL. I'm going with IL, so that'll be 12 IL. Are okay with that? Oh, 1.2. And here's what, 0.1, right? Are okay with that? Want to get that for loop 1? Yeah? Loop 2 now. Loop 2 here, right? We have 2 batteries, so I'm going in this direction here. Current will flow in that direction, so that's plus 14. But going against the 12, so that's minus 12. I'm going with IB, so that'll be 0.011 IB. And I am also going with IC, so that'll be 0.1 IC. And what IC is, I can substitute here. So this is 2 is equal to 0.011 IB plus 0.1 IC. So that'll be 0.1 by IL plus IB. So this is 0.011 IB plus 0.1 IL plus 0.1 IB. Add up these two, right? Add up these two here. I'll get 0.111 IB plus 0.1 IL. Right? I have my equation 1 here. I have equation 2. All right? We can make it look a little easier, right? We could try to, actually, let's just make IL the subject and substitute, right? I'll leave out the minus sign. Which part? Huh? Yeah. Right, so here what I'll do here, just to make it a little bit nicer, I'll multiply this equation by 10. So I'll get 20 is equal to 1.11 IB. 10 by 0.1 is 1, right? So it means that I can make IL the subject here. IL will be equal to 20 minus this. Right? 20 minus that. Right? I multiply everything by 10, right? Multiply this by 10. That'll become 20. That'll become that. That'll become 1. Right? So I'm going to substitute now. I'm going to put IL in here. So that'll be 12 is equal to minus 0.011 IB. If you wanted, right, to get rid of all the decimals, you can just multiply everything by 1,000. Right? And get rid of the decimals. But the value should be a little bit big. So that is 12 by this plus 1.2 by IL. I made IL the subject here. So that's 20 minus 1.11 IB. So this is 12 is equal to minus 0.011 IB. What's 1.2 by 20? 24. What's you can just do this, what's 1.2 by 1.11? 1.2 by 1.11. How much? 1.33? Huh? 1. Oh. Right, bring all the IBs together, carry this across. So that'll be this plus this. So that'll be 1.343 IB is equal to 12, right? I'm bringing that here and I'm carrying those two on that side. So IB is 12 divided by 1.343. What's that? 8 point? Anybody get that? 8.94? But then reach here? Why? Don't give up because it's decimals? Right? So you find IB, you have to find IL. About 8 normally. If I can just multiply it by, yeah, and then subtract. You get it value? Same value. How much is this here? What's this here? What IL is what? 10.1. Right? And when you add them up, that should give you IC. What is this here? Yeah. Right, but in different parts, right? You can't make an error here and carry forward in the same part, right? What's this? 19.1? Huh? Right, so that's the way you do a question, right? Are you okay with? Are you okay with developing the two equations? Okay, the equations wrong? Right, that's important, right? But don't take all the time in an exam and solve simultaneously. Okay, so just to solve simultaneously. Well, one thing I didn't get to do, I want to do before I give you a break. What give me a break for again? Your real time? Start back what time? Quarter past 10? No. Start back quarter past 10. Your real time again? Sit down. So you're gonna put 3.2. All right. I just want to run through the Wheatstone bridge. Right? I didn't get to do any like that, right? Let's take a look at the Wheatstone bridge here. Because remember, anything could go in the Wheatstone bridge, huh? Any of the transducers could go into the Wheatstone bridge. If they bring I'll say another thing again. It's what it's been trying to put a chance now. That break the spot for that. When it was in person, you can make people. Now it's online. But I used to stop that. Yeah, tired now when you were solving bar, but I'm not. Might again be 3 chance to stop that. But I did think. To get in. The equation, bro. Now, we'll say I'm after the equation. But the topic is not solving simultaneous. Do I want much? There's real help out here. There's real help out here. And how you get I1, I2, I3. You need that? Oh, yeah, did I want these questions to find I1, I2, I no. Well, you will get marks, you will get out of 8, you will get about 5. No, you wouldn't get none. Or you will get. No, but the equation's wrong. Yeah, not tonight. Right? That's about there, that's about 5. It's not much, but most of the marks comes from the up till there. What's up? Somebody has to get 5 years, no one saying enough. Huh? Somebody has to get. They will look how easy all this madness stuff is. Madness, you could get a graph. Huh? Okay, I think you could plug force versus magnetic strength. Remember any of the equations, you could just fix two bars, fix vary two, and fix it up. Any equation you can do that. Right, but based on like how chemistry one level petition for when nothing on unit 2 came. So I think I'm moving this here. First year, I remember there was a year that it was like that. They brought what they brought. They brought in module 3, they brought nuclear physics at Form 5. In module 1, they brought what they brought. Almost everything was Form 5. They brought something in like something in electricity and thing at module 2 they brought from logic. And it was mainly there was not much unit 2, mainly Form 5. All right, last thing, Wheatstone bridge, right? Right, it's a popular circuit. Last thing, and I'll give you a quick for a few minutes. Just a few minutes. No hour, boy. No hour. Right, Wheatstone bridge, right? That's a Wheatstone bridge here, right? And the Wheatstone bridge is generally used, right, when you see the voltmeter in the middle of the galvanometer, when that is 0, right? So you're basically using the Wheatstone bridge and making the adjustments until that reading, the voltmeter in the middle there, reading is 0. So if the voltmeter reading is 0, it means the potential at D and the potential at P equal. All right, that's the only way the voltage reading is 0, right? So if the potential difference at D here, if the potential difference here and here is the same, right? Oh, sorry, the potential there is the same. It means that the potential difference here and here also equals. That's okay? How you find PD, V is equals IR, all we need is current flowing here. Right? So we have the resistance already. Right? One thing you should remember is that Wheatstone bridge can be drawn like this. Right? Ignore this, huh? That's the picture I will get. Right? It's basically two potential dividers connected in parallel. That's okay? And by applying the same condition I told you, you'll be able to get this nice relationship here. So if you have 4 resistors, P, Q, R, and S, and you know P and Q, and you know R, you can find S. That's okay? And that's one of the main uses of the Wheatstone bridge. It's used to compare resistance or find unknown resistance values, right? That's okay? Let's just look back at the one from the last year now. Last thing, we're just looking on this last one here. Last thing. It was last year, 29. Right? Let's prove what we done. All we doing is proving this and we done. We're done. Done. We have to prove that. Oh, yeah, what's the zoom in again, right? Right? When the grid is balanced, the galvanometer reading is 0. Can prove that. Remember, first thing is starting with potential at X, potential at Y. Those potentials are 0. Sorry, equal. Right? So you have to find the PDs and then work it out. So that's fast. Last thing and again, I agree. The faster you do it, longer your break will be, right? It's starting back 1 o'clock. So you finish fast. 1 o'clock. 1 o'clock. Huh? Yeah, man, that's up there.
So when you guess we don't have
None. Do you think fast number?
this did not.
Sorry, no mark. Right? Just some small things you might need to add. Right? Just some small things. Right? I flow in here. When the current reaches here, it will split up. I1, I2. Right? And you'll also have the same current flowing here, I1, You'll have the same current here flowing I2, right? Because those two in series. Right? Remember we said since balance, right? Since it balance. Since it balance, we know that the potential at X is equal to the potential at Y. Right? So what we need to do, we have to find the potential difference here and the potential difference here. Right? And those two will be equal. So it means that I1 by R3 will be equal to I2 by R2. Right? So the PD across both of them, they're be equal. Huh? PD to be equal. The PD across here will be equal to the PD across here. And V is equal to IR, right? V is equal to IR. Do the same thing underneath here, potential here, and the potential here will be equal. So that'll be I1 by RL is equal to I2 by R1. Right? And now you can divide. Divide both of them, the i's will cancel, and you'll get R3 on RL is equal to R2 on R1. And what you have to do there, make R3 subject formula, R3. So R3, RL is subject. Are you sure? Yeah. RL will be equal to R3 by R1 all over R2. All right? And that's it. All you have to remember is this earlier. In a Wheatstone bridge, all you have to remember is this. In a Wheatstone bridge, the potential here and here is the same. Right? The only way that potential could be the same there at X and Y is that the PD here and the PD here is the same. So PD is equal to V by I, PD here, V by I. So we know that this is equal to this. And then do the same thing underneath. Potential difference here equal to potential difference here. Once you have that, you go to, right? Just divide and work it out. Right? The most important thing is you have to remember that when balanced, the potential X and Y is the same, and the galvanometer reading will be 0. And then from there, hopefully you can remember and fill up the rest. All right. Nice. Take a little break till 1 o'clock, and then we take a look at magnets. Online, or you can log back in. All right, let's go again. Magnets. Let's add point with one item. It was unmuted all the time. Right, so let's run through magnetic fields, right? Right, we need to be able to find the strength of a magnetic field, right? And let's call that magnetic flux. We need to find the force exerted on a particle in a magnetic field. We need to be able to obtain the magnetic flux density at different points, right? On different types of conductors. We also need to be able to see how particles behave in a magnetic field and so on, right? Ready? Ready. Sounds like a time when do that. Right, so a magnetic field defined as a region where magnetic forces experience. Right, we know that magnetic fields always leave the North Pole and come towards the South Pole. We should have an idea of the magnetic field lines and things, right? Electromagnetism is, for example, like if it's a force on a current carrying conductor, that force is dependent on a few things. So if you remember your Fleming's left-hand rule, you might remember this here. Right? Right. So if I were to take a magnetic field, right, and place a current carrying conductor and place a current carrying conductor in the magnetic field, that current carrying conductor will experience a force, right? And the force is given by Fleming's left-hand rule, force, magnetic field, current. Okay, just work it out from here. Force, magnetic field, current. Tell me what direction is the force on that conductor. Up, down, down, right? Down, right? Current going in, magnetic field north to south, so the forces downwards. So the force here is downwards. And the reason it's going downwards is that the magnetic fields are building up on top and forcing it to go downwards. All right? For that force, right? If I wanted to make that force larger, what can I do? There are three things I can do. Right? One we cannot take for granted. We need to make sure that the angles between here is 90. right? So to get a force, a maximum force, we have to make sure all the angles between everything is 90. We will also get a force here, right? If I were to adjust the angle slightly, we'll still get a force, but the force will be smaller, right? So the force, that magnetic force, is dependent on three main things. It's dependent on the strength of the magnetic field called flux density. It's dependent on the length of that conductor, and it's dependent on the current flowing in the conductor. And as a result, we have this nice relationship. F is equal to VIL sin theta, right? That's the way you find the force on a current carrying conductor in a magnetic field, right? V is the strength of the magnetic field, I is the current, L is the length of the wire, and theta is the angle. This force is maximum when theta is 90. All right? So it means that a force still exists when theta is not 90. Normally force is 0 when theta is what? 0, right? So it means that when it's parallel, when the current carrying conductor is parallel to the magnetic field, you will experience no force. Right? So we should know those things. Magnetic flux density, which is B, is measured in Tesla. Here we have an example of field lines, right? The north is where the magnetic field lines leaving, and south is where it's back in, right? Now, if we were to take now a magnetic field, and within the magnetic field, we place a charge, right? And of course, the charge will be stationary, the charge is moving. Then the force on that charged particle is given by the strength of the magnetic field, by the charge, by the velocity, sin theta. All right? So if I ask you to find the force on a charged particle moving in a magnetic field, that's what you'll do, right? And you'll also use left-hand rule to determine its direction. All you have to remember is that when using Fleming's left-hand rule, the middle finger direction of positive charge. All right? So if your positive charge entering the magnetic field, that will be the direction put up. If you have a negative charge entering the field, then your middle finger cannot go inwards, it will have to go outwards. All right? Because the middle finger points in the direction of positive charge. If a negative charge going this way, it means a positive charge going the next way. That's okay? So you have to remember those little things, right? As I said, we also need to be able to find the magnetic flux density around a straight conductor. That's the formula there. Oh wait, no, A missing. Right? It just B is equal to mu naught I over 2 pi A. That's it. That's the strength of the magnetic field around a straight conductor. A is the distance away from the conductor. So if I ask you what's the strength of the magnetic field right here, at that point, and I just need mu naught, that's based on the material it's in. I, current flowing here, and E, the perpendicular distance from the current carrying conductor to this point. Okay, direction there is given by right-hand grip rule and or screw rule, right? Both is same thing. Okay, so that's the way you find it there. If it's a flat coil, that's the formula. Mu naught Ni over 2R. Remember, R is the radius of the coil, right? Right, and it's the number of turns. Here, for a solenoid now, for a solenoid, the strength of the magnetic field is given by mu Ni. Right, and it's the number of turns per unit length. Right, so if you have 200 turns in a meter, N will be 200. Okay, you have to remember these little formulas, right? So if it's a solenoid, if it's a flat coil, or if it's a straight wire, you have to use the right formula to find strength. Magnetic flux density. right? Here we have two current carrying conductors and there's a force exerted. There's a force exerted on them. Please remember, whenever the current's in the same direction, the force is a force of traction. When the current's in opposite direction, it's a repulsion. Right? And basically, to find the force is equal to F is equal to PIL. That's okay? And to find P, what we're using to find P. What we're using to find the magnetic flux density. We're using the magnetic flux density for a straight conductor. That's okay? So if I ask you to find the force, all we need is current and then you work it out. Okay with that? So you remember when current in the same direction is a force of attraction and the force of repulsion when the current going in opposite direction. Right? Paul effect. Right? We need to find a way to find magnetic flux density. And there are two ways that we can find the magnetic flux density. The first way is to use Hall PD and use a probe that will give you the Hall PD. And the second way is what? Current balance, right? Current balance. So the whole effect is real simple. All we're really doing is this, right? All we're really doing is paying attention to the electrons. And when the electrons inside this material, there's a point in time called, right? There's a point in time when something called Hall PD is established. Hall PD is established when the electric force acting on the electrons is equal to the magnetic force on the electron. Right? When those two forces equal, you have your Hall PD. Right? Remember, electric force is equal to Q by E. But E again, capital E is what? Capital E, remember, if in an electric field, capital E is the electric field strength. If you're in a gravitational field, G is your gravitational field strength. If you're in a magnetic field, the strength of the magnetic field is what? What letter? Huh? What's the strength of a magnetic field? What letter? What? B, right? That's okay. So if I ask you to find the force is the charge by the strength of the electric field, and for charge particle movement is the strength of the magnetic field multiplied by the charge multiplied by its velocity. Right? And remember, electric field strength between two parallel plates is B on D. So if I make that substitution here, I can rearrange and I will be able to get Hall PD is equal to BV by D. Right? When is Hall PD observed again? Hall PD is observed when the electric force equal to the magnetic force acting on an electron. All right? And you have to remember how to find electric field strength and how to find, well, we know how to find it. Next part, right? Next thing, right? So basically, if I ask you to find Hall PD is BI over net. Right? The next option to find the strength of the magnetic field is what we call current balance. Real simple. We're taking a weight, right? The weight mg, and inside here we have a magnetic force. Right? We are adjusting two things that you can do. You can adjust the mass or you can adjust the distance here. Let's say we are adjusting the mass. Current balance says we're trying to adjust the mass until it equals to the magnetic force. That's okay? That's one option. The next option is to use principle of moments, right? Try to make sure the principle of moments here and here equal. Clockwise and anti-clockwise equal. Okay, so those are your two techniques for finding the strength of the magnetic field. Number one, using Hall PD, and number two, using the current balance. Right? Those are two techniques used to find the strength of the magnetic field. Right here, we have an example of something called cross fields. It might be difficult in this diagram, but try to ignore the magnetic field. Try to ignore the crosses, right? Try to ignore crosses. If I had a positive particle flowing through here, when it enters the electric field, it'll be attracted to negative. Correct? Yeah? Yeah. If now I were to add a magnetic field, that magnetic field will exert an upward force on the beam of electrons, and here what will happen? We'll be able to keep the forces equal, the upward magnetic force and the downward electric force. And if they equal, the particle or the beam of electrons will be able to go in a straight line. Right? That's something called cross fields. That's where you're applying a magnetic to electric or electric to magnetic. Anyone can do. That's okay? And again, it boils down to this. You have to remember how to find magnetic force and electric force. Are you okay with that? You gotta be able to find the electric force and the magnetic force. Right? What would happen if you do have a magnetic field? How you could create one? How you could create that magnetic field? By using electromagnetic induction, right? So that's where Faraday's law comes in and Lenz's law comes in, right? So we have something called magnetic flux. Magnetic flux. Right? Magnetic flux is P by A, that's density by the area. Right? The SI unit is Weber. There's something called flux linkage. Flux linkage is N by the magnetic flux. Right? N is basically the number of turns, right? So we have magnetic flux density, we have magnetic flux, and we have flux linkage. Okay? Three important quantities when it comes to electromagnetic induction. Right? So here's what Faraday said. Faraday said that the magnitude of EMF induced in a conductor is proportional to the rate of change of flux linkage. So basically, real simple. Right? If I have P lines and I have a conductor, and I move that conductor inside there real fast, the EMF induced here is large. The faster I move it, the bigger the EMF. Right? And Lenz basically said the direction of the induced EMF always opposes motion. So all of that is summarized into that little formula there. Right? Make a note of that. That's the formula used to find EMF. Rate of change of flux linkage. And the negative sign just showing it negative sign showing that it opposes motion. Right? A much simpler version is here. A much simpler version. Huh? Oh. What's up? Right? That's the way you find EMF. Rate of change of flux linkage. So you're basically measuring how fast the conductor cuts in the P lines. If we have a straight conductor looking like this, there's a much simpler version to find EMF. EMF is equal to BLX. B is the magnetic flux density, L is the length of the conductor, and BL. Yeah, that's true. Yeah. Exactly. BLV. Yep, BLV. Yeah. BLV, right? That's the way you find EMF, right? BLV. V is the velocity it's moving with. And the strength with a conductor of length L. right? And then you have your transformers, right? But we cannot do that already. That's a little transformer relationship, right? So to summarize, magnetic fields has to do with magnetic induction, right? When you're talking about magnetic induction, right, we have to also be able to talk about magnetic flux linkage, and how to find EMF using Faraday's and Lenz's law, right? We also need to be able to find the strength of a magnetic field, and there are two ways that we can do it. We can use a Hall PD, and we can use a current balance. That's two methods, right? Then we can also find the force exerted, right, on a current carrying conductor. And we can find the magnetic flux density in three cases: in a flat coil, in a solenoid, in a flat coil, and in a straight wire. And we know how to find the force exerted on particles. All right. Right, before we start in questions, let's try this fast. Let's try to write back over our summary. Number one, I'll call it things I want. Number one, let's try to write back our own summary without looking at anything, right? Number one, write the force exerted on a current carrying conductor. Number one, write the force exerted on a current carrying conductor. Write the force exerted on a current carrying conductor. Number two, write the force exerted on a charged particle moving through a force exerted on a charged particle moving through a magnetic field. Next, write the formula for magnetic flux density of a straight wire, of a flat coil, and of a solenoid. Write it. Each one. All right, next one. Next one is write what must happen for Hall PD to occur, and then make VH the subject of the formula. Find Hall PD. I need a little more space than my two lines. Write the condition for Hall PD to occur, and write the formula for Hall PD. Number whatever we reach. Right? And then write concept or write the formula for current balance. Right? So see if we can remember the condition for Hall PD to occur, and then use that to help find the formula for Hall PD. And then write the condition for current balance. Right? When you're done, write the formula for flux. Then flux linkage. And then EMF. Right, check it back now, see how much you got. Huh? There you go, all right. Wanna read it? Wanna read and write it down properly. All right, so let's see. Let's see if we can answer some questions now. Let's start here, do a little diagram, explain Fleming's left-hand rule. Fleming's left-hand rule. Left-hander. Do a little sketch. What is the rule for again? To find force, right? To find the force in a magnetic field for current carrying conductor, right? So you did a little diagram, do a little sketch, huh? You should draw your hand in the book and so again. Right, do a little sketch first. And then that comes, that's like 3 marks, right? By the way, what is one for? Very good, right? Right, but what you use this for? They all have the same meaning, but what is used for? Right hand. Yes, this is a drawing here. This one? What is for? Left hand is the motor rule, right hand is the generator. And generator is used to find current, right? Left hand rule, Fleming's left hand rule is used to find force. Fleming's right hand rule is used to find current. Okay, they all have the same meaning, but this one, force, this one, current. Right here, draw a diagram, label it up. Let's see what I get. Come on the board, if it's secret. Come on the board. Come on the board and draw it. Who's that there? Grant. Lock up on thing, go on and she'll lock up. Right. In Fleming's left hand rule, the middle finger direction of a what? Or a positive charge, right? Okay. Take a look at part B. You're done at part 1, part A, right? Take a look at part B. Take a little read and tell me what you think. Right, so you have an electron moving into a magnetic field. Complete figure 5 and draw the path. On the same diagram, draw the path of the electron if it's placed by a proton. Oh yeah. So one going one way, next one going the opposite direction, right? Oh yeah, draw a diagram. What do dots mean again? Magnetic field coming out, right? Oh yeah. Draw the proton and the electron. On the same diagram, work it out quick. Where you got, Alex? Up or down? Down? For the electron. So the proton is what? Up. Right, so let's see, I'll do it there. The magnetic field coming out. The magnetic field coming out. Right, going up. Already wrong. The left hand. Right? Right, I'll try and do it relative to this here, right? So magnetic field coming out of the paper, the current going where? This way. The electron going this way, so the positive charge going the next way. But this has to point the opposite way. That's okay? So therefore the force is upward. Yeah, what? Magnetic field coming out, so this finger pointing out, and the middle finger is the current direction or the positive charge direction. And according to that diagram, the positive going that way. So it means that the force is upwards. So the electron will go upwards and the positive charge will go downwards. That's okay? Kirchhoff? Huh? What? Yeah. Will the parts look identical? Right, the proton is heavier than the electron, right? So it will take a little bit longer before it gets pulls out. Are you okay with that? Are you okay with that? Yeah, so that's the proton and the electron, right? Make sure you can draw it, make sure you can work it out. The proton heavier than the electron, so the path will be a little bit longer. What's the work done? Part 2 and part 3. What is the work done on the electron as it passes through the magnetic field? Field. Try that there.
Yes. Yes.
Yeah. We all got to part 2. Huh? Huh? Part 2. Shabara, yeah. Part 2 as well. What you say the work done is? You have any bars to calculate? Not really, right? So it has to be what? 0 or something, right? High or something, right? What you all think? Which one you'll go with? So first thing you have to go with is what is work done? Work done is the force by the direction it moves in. The direction it moves. Oh, I said it wrong. Distance move in the direction of the force. That's okay? So what you all saying there? What do you all think then? But that's right up version of it here. That might help you. Right? If you remember that's right, work done is caused by the cosine theta. Right? The cosine theta distance in the direction of the distance in the direction of the force. Never think work done by distance? That's unit 1. Yeah, work done is forced by distance. But that's a charge on it. But in this case, you need this one. Right, what? Yeah. If the angle is 0, then plus 0 is what? Right. If the angle is 90. So here's what happening, right? But we had explained why the angle is 90. Right? If you remember the direction of the force and the direction of the magnetic field are what? Perpendicular. Right? So the direction they are perpendicular. So it means that the work done is equal to FD by cosine 90. Plus 90 is 0. So it means that the work done is 0. Right? The work done is 0. So write this down. The work done on an electron in a magnet. The work done by an electron. The work done by an electron moving in a magnetic field is 0. Since the magnetic field is perpendicular, since the magnetic field is perpendicular to the direction of the magnetic force. To the direction of the magnetic force. Full stop. And right out there, W is equal to D cos theta. Theta is equal to 90. Therefore, W is 0. W is 0. Right, side part 3. Right, when they talk about circular paths, well, what I remember, centripetal force, right? Centripetal force. More than likely, I might remember that. Right, so I'll just add that in here for you. Centripetal force is mv squared on r. All right, try that and see if we can prove that. Right, try using mv squared on r to see if we can prove that relationship there. So once you see circular motion, this here is your centripetal force. Part 3. What combined centripetal force? So what provides okay, quick. So what provides the centripetal force? What provides it? A magnetic force, right? So the magnetic force provided that centripetal force. So that magnetic force equal to centripetal force. Right? So the centripetal force provided is dependent on the magnetic force. Huh? Right, so we said that the centripetal force is mv squared on r, and we said that the centripetal force is provided by the magnetic force. Right, so magnetic force is equal to B QV, or in this case, the electron, so it's VEV. VEV is equal to mv squared on r. One of the V's will cancel, and you want to make r the subject. So you'll get R is equal to MV all over BE. That's all right. Are you okay with that? Chris, okay with that? Right? What would happen if the radius, sorry, what would happen if B is half? If you half B, look at the formula, what will happen to R? You make the strength weaker, right? So that will make R what? What will the part be? Will it be a smaller radius or a bigger radius? Bigger, because it will take longer to pull it out, right? Very had draw it. Right, be a little specific. How much bigger? Twice as big, right? Not 0.5. 0.5. So right, so if you put B as a half here, you work it out. When you flip it up, you'll get R is equal to 2MB on ME. All right, so you can go back to your diagram and just double your radius. Right, so your part might have looked something like that. Now we can double it up. Not looking like more than double. As the R there, right? Let me double up R. So that part a little bigger, right? You okay with that? Ruben, if follow while double?
Yes.
So Ruben, we come. Now catch myself. Ruel, sorry, Ruel. Ruben. I'm sorry. All right, nice. So the part will double up, right? And it makes sense, right? If the strength of the field weaker, it will take longer to pull it out. So the part wouldn't be as circular as the first one. Wouldn't be as sharp. It will be both will be circular. Take a little read here. Pressure here. Hopefully we have a formula to help us out there. Try that there from us. Use everything you learn. If you get that right, you're done. No, we can't go. Huh? Man, I think it's math or something. Don't worry about it. Try to get it. We'll pick up. With a math, I think it's math. Oh yeah. Work it out. Write down all the quantities there, Ruel. And let me see what you get. Huh? Yeah, boy. Big long paragraph. Oh yeah, I'll get frustrated. You want to read it. I like my little numbers. Integrators, differentiators, I have. I don't have plenty reader, you don't have to read all this. Right? So our electron is accelerated through our electric potential B. Right? So they kind of introduce something called electric potential now, right? The electron then enters a region of constant magnetic field perpendicular to the path. So they give us B, they give us B. In this region, the electron circular path is a radius of 10. So it's looking like we're going to use the path on top, right? It's looking like we know the radius and we can use the path on top. A next particle with the same charge, so the E value is the same, but with a mass mx. What was the mass the first time? Follows under the same conditions. If the radius is 15, find mx. Can you give us anything? But we have enough. We have enough. Right, call the first particle M1 or something, right? Oh no, it's an electron. Sorry, it's an electron. It's an electron. Right, more than likely the formula we're using here is what, Amanda? What we using? Which formula? What's it gonna say? One on top. Right? R is equal to mass by velocity by P on E. Right, now let's see what I come up with. Let's see how fine this 7 mass we can probably get. Huh? Sorry? What's the mass of an electron again? Yeah, part 3. What's the mass of an electron again? 9 point. By 10 to the what? 31 minus 31. Huh? Something so. All right, I'm about to after that. Right, the mass of the electron, you might need it. 9.11 by 10 to the minus 31. 9.11 by 10 to the minus 31. Oh yeah, try that very well. So the formula we use is R is equal to what? NV and MVB. Let's see how we get MX. I remember this what we have, right? R is equal to MV all over BE. Right? And they want us to find MX. MX is the mass of the particle, right? So that'll be R, B, E all over B. So we need R, we need B, we need E, and we need V. Right? Yeah. Somebody say we have R. Good. We have R. We have R, we have E. So we probably had to figure out B on V. BV, right? Try it. And you will, you might see this in exam, right? You got to be able to figure out what you're going to use, see what you have, right? You have this and you have this. So we had to figure out now how to get this. I need to try something. You know what R and what P. How we can get the PV. Check and see what are the quantities in there that remain. Which quantity? Which quantity there we didn't use earlier? The X-ray, yeah. And whole particles under the same conditions, right? There are two R. The R that we use in there is the one that corresponds to particle. In PU particle. Whole particle electron. Yeah, this one I'm talking about. This one here. Yeah, that's how it's going. So you gotta figure out how to get beyond. Right, so basically we knew that. Oh gosh, I forget. The first hour was what again? And the second hour 15. So this mx here has to do with the new particle. So it's 15 centimeters by the charge of an electron multiplied by B and V. Right, well? But we don't know what B and V are. So all we can do now, let's go back to the original part. So for the original part, you know that R is equal to mass of an electron by V all over E. Right? Can we make B and V the subject here? And we have R, and we know the mass of an electron and charge of an electron. So can we find B and V? Right? So like do a little rearranging, you'll get BER is equal to MV. So bring the V here. B on V is equal to ME on R. The mass of an electron is 9.11 by 10 to the minus 31. E is equal to 1.6 by 10 to the minus 19. And R is equal to 0.1. 10, right? So I use the earlier information and I found P and V. So you just take that and put it in there. So that'll be 0.15 by 9.11 by 10 to the minus 31. This will cancel with this all over 0.1. Right? That's the mass of particle X. When you do that, that will do that, and then you do that. About 13 or 14 or something. Much all again. So I found B and B, right? Now plug it in here. This will cancel with this, and end up with this. How much is this? 1 point? Right, so that gets 14 by 10 to the minus 31. Well, you got, and you got 1.37 by 10 to the minus 30. Yeah. I can round it up to 1.4, right? And I can just move it. So both same thing, right? I just average. Like 24. I don't know. I just have about 1, 2, 3, 4, 5. I don't really go more than 5 because I've answered. Let's go again. What you get this right? Yeah. Let's go again. Try that first part there. Everything there is straight from what we did. If you remember. Hey. Yeah, but I'm a believer. Oh yeah, try that there. Flux density. How you explain flux density? That's all? Huh? Yeah. So the strength of the magnetic field, but we could also rearrange this. So a more formal definition is from here. Right? What's the more formal definition again, Shabara? Yeah. So magnetic flux density. When a force of 1 Newton acts on a current carrying conductor with a current of 1 ampere flowing at an angle of 90 degrees. So magnetic flux density, just put 1 everywhere. Well, not 1 here, that'll be 90, right? So the magnetic flux density, right, is the force is when a force of 1 Newton is exerted on a conductor of 1 meter, carrying a current of 1 ampere, and at an angle of 90 degrees to each other. So just put 1, 1, 1, and 90 here. Right? And you'll be able to get the official definition. When a force of 1 Newton acts on a conductor of length 1 meter, carrying a current of 1 ampere. Let's put 1, 1, 1 here. 1 into 1 into 1 into 90. Huh? A conductor of length 1 meter. Carrying a current of 1 ampere. Right? Catching magnetic flux pattern on a straight wire. What will that be? No, the flux. Draw the diagram. What will it look like, well? What will the magnetic flux pattern along a straight wire look like? Yeah? 1 Tesla is 1 Tesla is when a force of 1 Newton, right? Here's how you remember any definition, right? From the formula, just put 1 everywhere. So 1 Tesla is when a force of 1 Newton acts on a conductor of length 1 meter with a current of 1 ampere flowing through it, right? That is 90 degrees that are perpendicular to each other, right? It does 90 degrees. Right? Just put 1 everywhere and put it into the center. Yeah. What do the field lines look like, Joel? What do the field lines look like along a current carrying conductor? Right? Say you then right hand grip rule, right? So there will be little circles like this. That's okay, little circles around the conductor, right? And the formula is what? B is equal to what? Right? Mu naught I by, well, in this case is what? 2 pi what? 2 pi r, right? 2 pi r. Right? Show that the forces between two pieces of wires given by that. how do we start working this out? I cannot talk to you about it already. But we starting with Andy. F is equal to what? Look at the formula on your sheet. Very good. F is equal to BIL. One of the currents to BI1, right? What missing there? How do I turn this into that? Right, just my battery. And you think about it now? What to do? Huh? And you think right there, boy. Substitute the flux density right there. You see that? See that? What's the name again? All right. Nice. So that's the way you work it out, right? But okay with that? So it will come together. It's somewhere in the head between now and Thursday, Wednesday it'll come together. It's somewhere floating around. The important thing is it's floating, right? But okay with that, right? Or they get those formulas, right? State whether, or is it a traction or propulsion? Why? Opposite direction. Oh Lord, you had to read all this. All right, Colin, read all that. I can't help all there. I can't help all there. I saw my questions are. But that's it there. All right. Tell me what it is. An example of a what? George. Example of a what? A what? No, it's not stereo. What is this one here? A current balance. Is it doing balance? Right? So more than likely that is a current balance. So you're looking. Huh? Yeah, but they give you a balance, so they probably measuring something else. Or you measuring the wire itself. Find the current through the wire. So I really can't help all you. I have to read that out. Some more here too. Actually, I might be able to find this one. 2005. But not all of them have this one. 2005. Right, so help out here, waiting on Shibara. She will help us out fast. If you finish, I'll get break. From Shibara. Get this one out first here. How do we find current through the wire? Take a little read, tell me what to do. Tap it close. Sorry? It's closed. Fresh stuff. Straight from the spring, up in the mountain. Up in the mountain. Huh? Which one? Which one? One there. Yeah, but if you break it, I'll fix it. Do you not cover it? Right. Ready, Sabara? The brake hinges on you, Sabara. Get that right, and we're done. You give me a small break and then we do some module 3. Well, I'll feel the same thing coming up. All the thing. Right, so it's a current balance. So all you need is weight and a magnetic force. Right? All you have to remember on current balance is some weight is equal to the magnetic force. And we know how to find magnetic force. Magnetic force is what again, Shabara? F is equal to BIL. Right? Let us see if we can find the things that we need there. Figure 6 shows a diagram of current balance. Let me read this one. Constructed in a following way. A 10 centimeter, where is that? A 10 centimeter long section of a wire is placed. It's placed on top of a pan of electronic balance, Leads are clipped, so we have leads there, right? So leads are clipped to the wire, running into a power supply, and through the power supply to another segment of the wire that is suspended directly. You'll see that? That is suspended directly above the wire and parallel to it. Right? So basically, you're seeing you have two wires with current in it, right?
Yeah.
You have two wires with current in it, right? One up above the other. The distance between the two wires is 2.5. So that kind of goes back to the formula that we just proved on top here, right? So of course, you will need that because they give you the distance R. You're seeing that? The power supply provides a current I running through the wires. The force on the lower wire is increased. The force on the lower wire is increased in the reading of the balance. When the power is switched on, the reading on the balance reaches 5 by 10 to the minus 6. How do we find I? It's a little different than this. How do we find I? So we identify the formula we're using. What we're using here. F is equal to mu naught I1 by I2 by the length of the wire all over 2 pi r. That's okay? Yeah, Alec? So we're using that, Alec. They want us now to find sorry? Right, look at what you have. Do you have mu naught? Do you have mu naught? Yeah? Do we have R? R is how much? And we have 2 pi, right? Do we have the length of the whole thing? Yeah, we have L. What we can say about I1 and I2? Very good, Andy. Tell Andy that. I1 is equal to I2, right? And do we know the force? Do we know the force? So can we find I? Can we find I? Right? See how simple it was? Right? So everything right there. This person filled up and it showed you exactly what to do, right? That one next part though. Right, we'll leave it out, right? I will let you work it out. Let's just talk it through. Or you can have them. The sensitivity and the balance is 0.1. Calculating minimum current detectable. How are we doing that? That one a little tricky. The sensitivity and the balance is 0.1 by 10 to the minus 6. How you will get the minimum current? And remember errors and sensitivity. And oh no. Sorry, you can ignore it. You know why? Because they take sensitivity off. But it's very similar to like error. It's very similar to errors. So you take the sensitivity and you multiply it by the you multiply it by current value that you got. Right? And you'll be able to get the max as well, the maximum minimum value. All right, let's just talk about part C then. Right, and I remember you all don't do this again. You're little errors alone in module one. Unit one. Right? They gave you what? What is that value there? Eden, what is that there? Tesla. That is your V value, right? Yeah. They give you the radius R and they give you the length L. Right? The wire carries a current, they give you I. How you finding the number of turns per unit length? How you finding the number of turns per unit length? Use the formula for what? Flux density, right? Which is what? P is equal to V naught Ni. N is the number of turns per unit length. Right? And then when you know N, how you get L. Right? If you know the number of turns, wait, I do not have part. Or they want the full length. So they want the full length of the entire wire. What you have to do? Huh? This first formula here? No. They won't do that. After you get the number of turns, you have something to do. You have to multiply. You have to find the circumference and multiply it out. Right? Watch it here. If you have all these turns, right? If you have all the turns to get the length of the whole wire, you're taking the number of turns, let's pretend it's 10, and then you're multiplying it by the circumference of each one. And that will give you the length of the wire. 2 pi r. 2 pi r, and they give you r. All right, right, no break, module 3. Let's start one time. One time, because Adam is going to module 3 one time. Right, module 3 is made up of what? No break. All right, half an hour and then module 3. And if it's tired, don't go and get up and go and pick cards, right? Take a rest. Half an hour. And don't play waking up now, eh? Don't play waking up now and then going back and sleep. So, yeah, next chapter.
I'm like going to upload soon.
Both sides of the random. Okay, right. Alright, let's go. Good, where am I run? Alright, let's start. Alright, we can start. Let's go. Beer. That was really last one. Last play, one. Right, so let's see how much you remember in module 3. Module 3. Have you started now? You're joining. Alright, so I'm starting, right? Alright, let's start. Remember, if I can see all the way back. First place. Without one person coming to put the wrong thing. One person pressing green for everything. Does anyone just there? One person here. Everything have both, right? Particles have both properties. One on one answer, right? Alex, problem. Sharice and Karina. Oh, Karina online. If you get too much wrong, then it's better. Yeah, it's a fully target, but it also has a conductor. So I can put both of them. No, no. I should have been red and green. Huh? That should be red and green, but I don't know, do I mix it up one after the other? How are you see there? Top 5 not changing, boy. And that was one. Not changing at all. He done fighting up here, but he done fighting up on the outside. Adam, am I? Listen. Two more to go. Like, it didn't come out too good. Just here. Now, one person might consist of that's interesting. But that's fine. Now, I want to find who that person is really great. Right, we're going on in here. I feel like going here. Two of them going. We will fighting up with two there. Last one, no double points, so. Yeah, but. Get on, boys. Let's see how it changes up, but we know it's up to it. It's up and here. It's one, two. That one. Three stated. That's all. Yeah, that one next one. That's the one. That would be so fun. Alright, I want to log into the next one after. Let's take a look at module 3. I want to log into the next one to see if I find. What? Break for one, huh? Right, so module 3, photoelectric effect came recently, but we just run through it as well. And two of the things that didn't really come for a while, X-rays and electrons. And then of course, stability, right? Right, but let's just run through it. Remember, the first part of module 3 basically talks about quantization, right? Or the particle effects. So basically, photoelectric effects, if it hits a metal at the right frequency or the right amount of energy, electrons will leave. And those electrons that leave from the metal, they will leave with a particular amount of energy. Right? Einstein proposed that right? Einstein basically proposed this, right? He said that the energy of the incoming radiation went towards breaking the bonds for the work function, and the remaining was the kinetic energy. So he said that by using Planck constant, he said that HF was equal to HF naught plus EVS. Vs is the stopping potential, F naught is the threshold frequency. That's the minimum frequency required for the whole process to happen. And this here is the frequency of the incident radiation. All right. But of course, if the frequency is less than F naught, nothing will happen. Right? Frequency has to be more than F naught for the entire process to happen. So Einstein summarized the whole photoelectric effect by saying this. All right, everything is summarized by that. Right? these were some of the problems that could not be explained using classical physics. So Einstein proposed those relationships and he fixed it. The main thing he did, he said, well, here's what light. Light is not made up of waves alone. Light is also made up of photons. So he introduced something called the particle nature of light. Right? So that was basically a photoelectric effect. Something popular in graphs, you have to be able to take that one formula and rearrange it, creating the form y is mx plus c. Right? Here I have two examples of being able to rearrange that, right? Right? So three examples. Three examples of different graphs that could come. Okay, that's a photoelectric effect. The next thing we'll talk about is something called wave-particle duality. That is where de Broglie was able to show that light has, right? That light has both properties, right? Light has both particle and wave properties. Here we show that, here he was able to show that a wavelength is dependent on a particle property. P is what again? P is momentum, right? So therefore the wavelength called de Broglie's wavelength is Planck's constant over momentum. Please remember momentum is mass by velocity. So momentum is really, it's strictly momentum is mainly a wave property. Sorry, particle property. So this one little relationship was able to show that that light has those two properties, right? How did we show it again? Well, basically, remember, E is equal to mc squared and E is equal to hf. Treat them and you'll be able to get it. Right? So if at any point in any question they ask you to find de Broglie's wavelength, you have to apply Planck constant by the mass of the particle by the speed it's moving at. Yeah? What's that? No. But I tell you spell it properly. Right? So basically that's something you need to remember. Here we have an example of the line spectra. The line spectra again was able to show quantization, right? It was able to show if you want to move from one energy state to the next, you have to lose an exact amount of energy. Electrons don't exist in the middle. Electrons only exist at these energy levels. And to go from one to the next, you have to lose an exact amount of energy, right? Take the energy level here and minus them, right? And you'll be able to figure out how much energy is lost. Or are we given off? Right? X-ray production. X-ray production is very similar to photoelectric effects, right? You have electrons and the electrons knocking. When the incident electrons hit a target metal, what has happened is that electrons will leave from one energy level to the next. And as a result of going from one energy level to the next, it gives off energy. And that energy is in the form of X-rays. All right? You may have remembered in Kahoot that those X-rays are dependent on the voltage here. All right? So X-rays here, very, very important. This line here. If I ask you to calculate the wavelength of the most energetic X-rays, you have to take the voltage and find the energy that voltage will give off. And you have to make the assumption that the electrons who lose all their kinetic energy will produce the most energetic X-rays. So you take the energy by using E by V, and you use that to find your wavelength. E is equal to hc on lambda. All right. How you find E? E is equal to E by V of Q by V. Right? That will give you the energy of these. That will give you the energy of these that the electrons lose it. Right? And once you have the energy, you can come here and find the wavelength, right? Here you have properties of X-rays. And here you have some uses of X-rays, right? The X-ray spectrum has two parts, the background, right? That has the nice smooth part. I'll show you that now. Well, you should be able to draw it, right? Background radiation, where the minimum wavelength depends on the operating voltage, and the very intense happens at specific wavelengths. And these wavelengths are dependent on the target material. Here is the diagram, the continuous, the smooth part, and the little spikes, right? The little spikes are what they're talking about here, right? The very intense emissions. Anybody remember how we get those very intense emissions? That's when the electrons knock out very deep lying electrons. So when they knock out deep lying electrons, right, from the energy levels, and something takes its place, the energy given off in the form of those X-rays. All right. Right. Next thing we have to learn about is something called X-ray absorption. Right. It's quite popular in questions. If I give you a material, of thickness X, and it have X-rays of incidence, of intensity I naught, some of the X-rays are absorbed. Right. So a particular value I is given off. And that value I is dependent on the coefficients of thickness in there. So I is equal to I naught by E to the minus mu X. Mu is coefficients of absorption. I naught is your original intensity, X is the thickness, and I is the intensity coming out. All right. So this attenuation formula here is what we use to determine the intensity of the beam after it comes out of the material. All right, so in X-rays, two most important, well, some of the important things, you have to be able to describe how the X-rays are produced. You have to be able to explain the two parts of it, the continuous and the intense part, right? And you have to be able to find the wavelength. You have to be able to find the wavelength of the X-rays, right? Please remember to find the energy of the X-rays is equal to Q by V, right? And then you need to be able to find the intensity of an X-ray as it passes through some material, right? And of course, we'll know the uses and thing of an X-ray. Right, very important. This is what you might see on your exam, right? Right, other than X-rays, something missing. What missing earlier? What missing? There is something that's missing that shows quantization again. That shows particle nature. Guy. Huh? Who's the guy? Millikan. Right? Now in there. So here's what Millikan did, right? Millikan took a charged oil drop and it dropped it between electric plates. All right. And what he was able to show was this. He was able at some point in time. He was able at some point in time to stop the electron. Sorry, to stop the oil drop. The oil drop is negative charge, right? So the forces acting on the oil drop when it's stationary would have been weight and the electric force. That's okay. When he kept it stationary, both of them was equal. Right, Jude? Both of them were equal. And then we're to use that relationship to find Q. What's the formula for electric force again? Where? We use it all here. What is it? It's charged by electric field strength, right? And the electric field strength between two parallel plates is what? Is V on D, right? V is the voltage and D is separation. And we know what weight is, mass by gravity. How you found the mass again from the Kahoot? How we found the mass? We found the mass by finding it by finding the period of time when the oil drop was falling through terminal velocity. All right, and we use that to help find the mass of the object. Now, what is terminal velocity? Terminal velocity is when the resultant force is what? 0. Right? All the forces acting, the resultant is 0. And from here, you can rearrange and find Q. That's up on there. Or that the consequent let me what? But can I use that? Yeah, I can't do it. Right, so mgd on v. Right, and anybody remember what Millikan was able to show? Millikan was able to show that Q is what? Huh? K by E. He was able to show that no matter what charge you get on the oil drop, it's a multiple of E. Right? But E got? What E? Right, E charge by electron, right? So Millikan was able to show that the charge of this oil drop is always a multiple of E. He was also able to kind of work out the charge of one electron. All right, so that's what Millikan, and that is what X-ray is about. Those are the two possible things that could come here, right? What remaining is X-ray. I mean radioactivity, right? Right, let's run through radioactivity and do a couple of questions, right? We're doing Millikan and X-rays first, right? Right, radioactivity, you have alpha, beta, gamma. Right? I hope you remember what's alpha. What's alpha? A helium atom, right? Beta is what? Beta is an electron and gamma is pure energy, right? You gotta be able to balance reactions, make sure the mass numbers on both sides equal. Right? You gotta remember the properties of alpha, beta, gamma. Alpha is normally go up, gamma is go straight through, beta is go down. Right? And but you just find it in case you forgot, you could use Fleming's left-hand rule, right? You could use Fleming's left-hand rule to work out all those directions, except for gamma, right? Here we have electric fields. Alpha goes towards the negative, gamma is undeviated, beta is towards positive. Right? We have to know about radioisotopes and their uses. And we have decay curves and find the half-life. How is finding half-life again? From a decay curve. Take a reading, let's say 100, and then find the reading for half of that. And minus it 2 times, right? Take 50, take 25, find the times and minus it. Right, Viv? You're smiling. Right? Activity, right? We did it in Kahoot and you'll guessed it correctly. Right? Activity is the rate of decay. Right? So the number of disintegrations per unit time. Activity is given by minus lambda n. Minus means it's decaying, right? You can also have A naught minus lambda n naught. And then if you integrate this, you will end up with the radioactive decay formula. N is equal to N naught by E to the minus lambda T, or A is equal to A naught E to the minus lambda T. Lambda is what again? Lambda is something called your decay constant, right? And then we could use lambda to help figure out half-life. Right? You gotta be able to prove that, right? Take ln on both sides and you'll be able to get lambda is equal to ln 2 on half-life, or half-life is equal to ln 2 on lambda. But if you're not, So those are my things that we need to remember, right? If they ask you to prove it, they won't ask you the integration part. But I won't say they won't. But the main part that you have to prove is this part here, right? They like to ask you to prove half-life, right? So all you have to do is just put n naught on 2, n is n naught on 2, and t is half-life, but take a little ln on both sides and work it out. All right, that's it. Take a look quick. Are you happy there? Next one. Question time. Let's start with Millicott. Millie, where are you, Millie? Right. Let's start here. You don't really have much. You may have done this already. So you can get it right, right? Take a little read. Let's see what you get. Right, take a little read. Oh yeah, come on. And then I'll get take a little read. Already forced deduction on it. Always remember in the question there is upthrust acting, right? But we're going to see about the upthrust. Why we leave it out? Because it's negligible, right? And the reason is that the density of air is negligible when compared to that one. So the upthrust value is small. So you can leave it out. Go ahead, have fun, work it out there. The washroom downstairs open. Yeah. Why would the people? Right? Draw the forces acting there. Write down the values first. Let me just zoom up there for you. Huh? Now, this didn't come with the part 3 years. This one actually didn't come. You didn't pay attention at the beginning when I was showing you. Yeah. Write down the values, let's work it out. Come here, let's work out. Grant, come now, you got 6 or 5 hours already. Come on. Should be good there. Write down the values. They gave you a value of D, they gave you the mass of the drop, they gave you the voltage. Oh yeah, do your thing fast. Let's work this out. I'm well. Right? Put in the forces and then let's go to the question, right? You have the voltage, you have the right. What's the main thing here? When you keep it stationary, what's happen? When you keep the oil drop stationary, right? The weight is equal to the so remember no upthrust. Weight equal to the electric force, right? Weight equal to the electric force, right? All right, let's go. Try the calculation there. Right? Find the charge of the oil drop. Same thing, make that equal to that, substitute, work it out. Same formula, just give it the result. Just give it right now. Huh? But yeah, this was work it out, tell you after. Work it out and tell you after. You don't have much. Right? So we said that what? We said that the weight was equal to the electric force. And I gave you the formula for electric force. And remember, E is what? What E again? Huh? beyond. Right, go ahead. Work it out fast, find the Q. Come away again. Okay, work it out. Yeah, work it out. Plug in the values that is showing up. Right to the next part. So let's start that quick. Even up. Boy, was paying attention. Oh yeah, work it up quick. Finance Q. Finance 4. Finance 4. 4. Finance 4. 4. What are the values, right? You got the values? Oh yeah. Find those two parts there, and then you have a last part 3 there. Huh? Are you finding part B? I don't know. If you have the chart. Or you get number of electrons. Like if you have the chart. How much shall I get? Right, so when you rearrange here, you'll get what I replacing this with V on D, right? So you're going to get Q is equal to mgd all over V. So the mass was what? 9.8 by, right? Gravity is 9.81. D was what? 1.5 by 10 to the minus 2. Huh? Minus 2, right? And P is what? 1.5 by 10 to the 3, right? So the value was 1500, right? So we just using this relationship here. All you have to remember in Millikan is that he stopped the oil drop and he allowed the oil drop to be stationary. So those two forces equal, right? You have an oil drop, you have the electric force here, and you have the weight here. right? The electric force is positive here, down here negative, right? Right? So when you work this out, we got Q to be what? 9.6 by. And if you know the charge, I told you that Q is equal to KE. So to find the number of electrons, this K is equal to 9.6 by 10 to the minus 19 over 1.6 by 10 to the minus 19. And you all got 6. 6 electrons stuck on to the that thing there. That's okay? Next part. What's the next part, Andy? What happened to the next part? What's the next part there? So here is no longer positive, it's now what? Now negative. So the electric force will be acting where? Up or down? If this negative, will it be attracted to this? So the electric force now acting. That's okay. What do you want? What do you want? Acceleration, right? What is find acceleration? Acceleration is the Fy resultant force by M, right? Over M. What's the resultant force acting here? What's the resultant force acting on the oil drop now? You done? What do you think? What's the resultant? Any upward forces? Right now? Any upward forces? No. So it's what? This plus this. And we know the mass, right? That's okay? The question changed a little bit now. It starts to fall. Right? Of course, they could include drag force and then in the next question, right? Where you have to find the resultant minus this some drag force. Right? So we have other possibilities as well. But when the question asks for acceleration, you know acceleration is resultant force and mass. You know what the mass is, so all you have to figure out in the diagram is what is the resultant force. Right? That's a milliton. Let's do our experience. Huh? What's up? Yeah, you gotta work it out. You have to wait and you gotta find back the electric force. And you work it out already? You gotta find back this E by Q. Yeah, and work it out. Same values they use, same values. Force is this is the force. Electric field strength by Q. And you know Q now? Right. And electric force is the voltage over the distance. So multiply this by a Q value and add it to your waves. Some more again. You guys follow what to do? Yeah? Kirchhoff? All right, let's go again. Finish. How about it? Huh? Watch it. Okay. 1.28 by 10 to the minus 16. बढ़िया क्या बढ़िया हाँ follow up. Right, so acceleration. So the acceleration is the resultant force on the mass. We have to find the resultant force, right? That'll be the weight plus the electric force. Right? The weight is 9.81 by 9.81 by 10 to the minus 15 by 9.81 plus the electric force. The electric force is Q, which is 9.6 by 10 to the minus 19 by V on D. V is 15. V and 1500 over 1.5 by 10 to the minus 2. When you add this value up, that's the resultant force. About what? The minus just showing you, the minus just showing you that the polarity here changed. We know the acceleration is downwards. Right? Technically what? Technically this charge is negative. So they can cancel out. Right? Right? And then you divide it by, right? You divide it by the mass, which is 9.81 by 10 to the minus 15. That thing there, that would be bada bing, bada bing. What is that? What is that? Check it back. Yeah, so it should be around 9 point something. What you got, Andy? One says here. Oh, anybody getting issues using this calculator in school? No? No, I've seen at school since they going to take away all the calculators. Huh? The same programmable. How much you got? Yeah, something like that. 19.6? 19.6. Huh? What? 9 point? Oh my God. Oh my gosh. Oh my gosh. I'm sorry. Yeah, you know? I do not. Yeah, no. Are you okay with that? Next one, X-ray. Right, just put it just like it's in the calculator. Just like this in the calculator. All right, let's take a look at the some X-rays there first. Yeah, next one there. What you can say there, mu is what? Very good. What is mu is? Huh? Answer is D, linear absorption, right? Yeah, real close. Real close to the wrong thing. Next one is what? Mu is what? See if we get this one. Huh? All right, no, yeah. I thought it was a calculation. Sorry. Try this one here. Let's do it. Top up the voltages. The voltage is 90 kilovolts. Current is 1.2. Huh? Yeah, that was it. Right on the thing now, right? Right on the thing now, right? And try to work it out. 50 kilovolts, 1.2 milliamperes. Can we go? Well, okay with that? All doing good, all doing good. Go ahead, have fun. Huh? Yeah, you can break that down. Have fun. 6 rounds. Nobody. Nobody. Nobody, nobody, no. Oh yeah. Do that fast. That's crazy. Happy now? Oh yeah, do that fast. Quick as you would. Quick as you would.
Yes.
Milliamperes. Finished? Oh yeah, find the power. Power is what, Andy? Right. How you going to find speed? Speed is what? Yeah. How is your find speed, Andy? Besides distance over time. How is it can find speed? When you get 3 in a row, I'll be getting up down that. What? Find speed. What else we can do? Chibara, what we can do to find speed? Chibani, how we getting speed? How velocity formula? Drift velocity. Yeah, we have enough things to find out. We have the voltage. Can we do anything with the voltage? If you have the voltage, the operating voltage, what you can find? It's an exit question. What you can find? You can find it. What is it? Energy, yeah, you can find the energy.
Yes.
Right? And if you know the energy, how you can find velocity? E is equal to a half mv squared, right? E is equal to a half mv squared. Huh? A half mv squared, yeah, make me the subject. Oh yeah, find the energy and work it out, and then find the wavelength. We want one.
Yeah.
Right now, yeah. What? Huh? No, just the last one. Let's do it again. Second. No. So power is equal to I by V. I was 1.2 by 10 to the minus 3, and your voltage is 50 by 10 to the 3. So that will cancel, you'll get that will do that, and then you will get 60. And you'll get 60 watts. Then part 2, they want us to find the speed. So we're going to try to use kinetic energy is equal to half mv squared. Right? So V is equal to 2 by the kinetic energy all over the mass, and then we square root it out. So let's see if we can find the energy. Right? We square root in 2. Energy is equal to what? Right? We know that energy or work is equal to Q by V. Right? It's electrons, right? Yeah. It's electrons, so that'll be 1.6 by 10 to the minus 19. Right? That's the charge by the voltage is 50 by 10 to the 3. All over the mass of an electron, right? The mass of an electron is 9.11 by 10 to the minus 31. When you work out that, you will get its speed. How much is that? 1.32 by 10 to the 8. All right. Remember to get more than the speed of light somewhere around, right? Close to it, but going fast. Fast, fast, fast. Really, really fast. And part 3, how we getting the wavelength here in our graph? Each, let's see. Let's spell your name right now. You like that? Lambda is what? HC over E. What's H again? 6.63 by 10 to the minus. But you can't write Planck's constant here. So that is 3 by 10 to the 8 all over E. Oh, shucks. I didn't work out E. I just have to write this, right? 1.6 by 10 to the minus 19. 50 by 10 to the 3. Right? We didn't physically work it out. How much is that for the wavelength? It should be in the nanometer range, right? Well, no, smaller than that. Wavelength is what? 10. X-ray is what? 10 to the minus 12, 13, somewhere around there. 2.48 by 10 to the minus 11. So X-ray is around minus 12. All right. So it should be sort of realistic, right? Remember, it's for X-ray. So your value should be close to that. Huh? No, I'll have to log into the next one. I'll learn to teach them the next one. Anyway, I'm gonna see if you know you. Huh? No. If he logged in now, I wouldn't get you. Right, so that's the X-ray, that's a Millicon. What do you want to do now? Busting down, we are thinking still. Oh, we didn't do attenuation. What was the last time we did? So that's 2016. Nobody wanna see us together. Push up the book that we happily fall out here. Nobody. There's 2014, right? Nobody wanna see us together. Right, the first part explain how X-ray is produced, right? I'll even know that. Try this here, 2014 B and C. Last one, then I'll give you a quick. How we can stop. What do I want to do? Funny. Work out that. If you get 2 of them right, you stop it. That's it. Get 2 of them. That's what they teach us. Oh yeah, find the energy of the active photon and then do the last part. Last thing, and I'll give you a Oh yeah, well, come on, boy, I mean, part one, I need to part of the Nothing now we go. I mean, people are angry. Yeah, we want to find energy, it's on the board. It's on the board. It's your alarm. Hurry up, find E. E is equal to AC on lambda, yeah, B, yeah, B, yeah. Fast. What's not going to be the last part? I equal to oh yeah, put that and get a little bit. Oh yeah. Yeah, come on, hurry up now. You find it also. This is the way I have that's it. And the way I have just one. Beginning of March, you can see that news. Nobody wanna. Right, Antonio. Antonio will do this one for us all.
Let me tell you something. Let me tell you something.
You have to do it.
Let me tell you something.
You have to do it. Pardon me, ma'am? You have to be in your ma'am. Yes. What's the formula with divine energy? What? Still on the board. Right? Antonio said E is equal to HC on lambda. Right? H is 6.63 by 10 to the minus 34. C is the speed of light. And lambda was 10 to the minus 11. How much you get? How much? 3.198? 1.98 by minus 40. Right? That's part one. Now we talk. See, how I catch you. What you have to do? Convert to electron volts, right? So you divide by 1.6 by 10 to the minus 19. How much is that? Sorry, sir? Yes, sir. You want to find out how much electron volts? Your value should be. How much you got? Oh, you must. 1 point. How much? 1.24 by 10 to the 5 electron volts. Right? If it's mega electron volts, right? That's the value in mega electron volts, right? Part 2, what's the formula we're using in part 2? I is equal to I naught e to the minus, right? Let's see what they gave us. They gave us mu as 0.3. They gave us mu as 0.3. And they gave us, that's it? Oh no, they said what is thickness? So they want to know what is x, right? What is x? If the intensity of the beam, it goes to 1% of the original, right? So 1% of, so I is now 1% of I naught, right? Plug it in here and work it out. 1% of I naught is equal to I naught e to the minus 0.3 by x. I'll leave it like that on how just get my answer in centimeters and then I can convert it. Right? The I naught will cancel, take ln on both sides. You will get ln of 0.1. You will get ln of e, and ln of e is what? Ln of e is 1, right? So you will get minus 0.3 t is equal to ln 0.01. Work it out and you'll get t is ln 0.01 over minus 0.3. But I like that, excellent here. So X is how much? How much? Centimeters, right? 15.35 centimeters. That's okay? Right? Take a little break, half an hour till 5, then we take a look at the missing things, right? Right? Anybody want some of the coffee? I just want to open it up fast, right? Free, yeah, free. Oh, free, yeah. Anybody want this? Five more than one. Yeah, free, yeah, all the parent thing.
Yeah. Is it? Well, that's not good. Yeah, it's all. Well, they actually. Yeah.
Op amps.
是。因为把这个录完了这个，到时候晒了这个视频，我是不让人去这个。
Are you over?
我把这个录完了。
How much you have paid?
Because you said it is still most people and you can think of the top.
We part.
You are
Yes. Hey, you gotta think out over part. All right, let's go. So let's take a look at op amps, right? Yeah. Everything else goes again like that. And the question, right? Yeah, so right? No question. All right, let's go again. Right, so we want to take a quick look at op amps. Right. Here you have a Wheatstone missing. Madam. And just go like my boss. So be ready. Somebody send up something I can say now outside. All right, so that there is your basic op amp, right? Right? Your op amp is basically a transistor. That's one of the functions of a transistor there. Come in, Andy. Come in. Right, so the op amp basically looks like that, right? The op amp has two inputs, a positive and negative, but what those inputs really imply this, right? It has a non-inverting op amp and an inverting, non-inverting terminal and an inverting terminal, right? What the op amp basically does, it takes a small input and it gives you a large output. And the ratio of output over input is called the what? Right? And your gain cannot be big, your output cannot be bigger than what? Than the supply value, and it cannot be smaller than your minus supply, right? And right, what would happen if the value is outside of those range? Saturation, right? So because of that, we know the general shape of the op-amp. How does it look? General shape of the op-amp is up like a little Z, right? What type of op-amp is that? Non-inverting or inverting? Non-inverting, right? If it were inverting, it will look like this. Right? That's the general shape for the op-amp. Right? That's the graph of V out and V in. What's the horizontal parts again? Right? The horizontal parts are saturation and the slope parts are what? The slope parts are where you can find the gain. All right? So everything is seen there, everything is seen in front of you there. That is basically all the components of the op-amp. You have output, input, and you have a supply. The supply is the largest possible output. Right? If you look at this example here, that's the general shape of op-amp. That's a non-inverting op-amp. All right? If you look here, you have the three ideal assumptions of an op-amp. Op-amps are infinite open loop gain. Right? Infinite. What is impedance again? Right? Impedance means resistance, right? High input impedance, low output impedance. Right? And that's some general rules on the op-amp, right? How to find gain, how to show saturation, and how to find the inputs that will cause saturation. All right? That's how you find the input that will cause saturation. What does this graph show again? Right? It shows the graph of how gain and frequency operate, right? Right? What do they call it? Bandwidth again? Right? Bandwidth is the range of operational frequency. So for example, at your open loop gain, that's your highest possible gain. The bandwidth is 1 to that value. Are you okay with that? Right? At your closed loop gain, that's lower down. This is the bandwidth here. And unity gain is what? Unity gain is when the gain is 1, right? So the bandwidth is the entire length here. What you'll recognize as the lower the gain, higher the bandwidth, right? So the op-amp becomes more functional as a larger range of frequencies to root for, right? So that is the op-amp, right? You have 3 types of op-amp. Number one is the what? Number one is the, what is called an op-amp? Very wrong. Wrong. A comparator. No resistors, right? See any resistors there? No resistors. Comparator. What does a comparator do? Compares. Okay there? If Vn is more than V reference, high. Vn is less than V reference, minus. Right? And let Vn and V reference here. So just do me a favor, I'm gonna write some values here. Tell me what the output. Here is plus 12, here is minus 12, here is 4 volts, and here is 3 volts. What's the output? Positive 12 or negative 12? Positive 12 because in non-inverting bigger than the inverting. All right? Right, that's here. This value here bigger than this value here. So saturate high. Just do one more little favor. We like to bring the graphical version, right? Right, what you there? You have 2 inputs graphically. You have 2 inputs going into op-amp. What's the output look like? What the first thing is do again, they did a question like this. Draw the little broken line where they intersect, right? Right. So we have those two inputs, the red and the blue, going into a comparator. What does the graph look like? Look at the red and look at the blue. Which one larger?
Red.
The red larger, right? So if the red larger than the blue, okay, then since there wasn't time there, what's the answer? My time the answer there. The red bigger than the blue. The red is the inverted. If the inverted more than the non-inverted, the answer is what? High or low? Low. Right? The answer is no either. It's low. What was the next one? The blue bigger than the red. High or low? High. The red bigger than the blue. Low. Right? So your graph will look like that. Please remember to draw the broken lines over where the two inputs meet, right? And then figure it out. Right, Shabara? So that's your first type of op-amp, that is called a comparator. The next two are the inverting and the non-inverting. How you know the difference here? Negative, nice. So if you look here, how is not inverted? Number one, we have resistors, and number two, the non-inverted or positive terminal connected to it. And this is the formula for gain. Right? That's the formula for gain of an inverting op-amp. Right? Remember, I showed you how to prove it, find B out and B in and divide them, right? And then for a non-inverting op-amp, again, resistors, and the negative is connected to it. All right, that's how you know a non-inverting op-amp. And down here is your formula for gain. Okay, so you have to know gain for both op-amps, right? So the three types of op-amps are what? Comparator that compares values, non-inverting op-amp with that gain, and inverting op-amp with the minus RF and RN. Anybody remember the special application of the inverting op-amp? The summing amplifier, right? And this here is the equation for the summing amplifier. Okay, the summing, what's the special property of the summing amplifier? It has the ability to take three inputs and give you one output. All right. So it can take three inputs and give you one analog output. So it can take three digital and give you one analog output. All right. So theory-wise, those are the things that you need to know for op-amps. All right. Now close the book and write a summary for module 1 to 3. 1 to 3, yeah. 1 to 3. Go ahead, start now. Write the person with the best summary within $200. Close the book. What's up? Everybody okay with that? So basically, that's the module 3. Make sure you spend some time and go over all these things, right?
Okay.
I'll want to do a question, anything in particular? No, I log himself, so I can't get into the upper. That's my password, so I can't put them out. All right, do some more. What the paper want to look at again? Huh? 2019. Which one? 22. Right? Let's just go to 2022. Right? Of course, spend some time in 2019 as well, right? 2019 was the peak for unit 1. Right, so you want to run through a few things. Can you prove this?
Yes.
How do you read it? Right, two resistors in series and you work it out, right? Right, write the formula for that, so you can handle that. How are you doing that? Huh? Right, you can use Kirchhoff's law or you can apply the resistance and work find the total resistance, right? Alright, that can work. And then if you plot the graph, well, you please take your time with the unit something on the graph, right? When you're plotting your graph, make sure everything in you read up your values properly, right? This one's straightforward. Right? And when you're linearizing, take your time and linearize. Question. If you plot a graph of IL versus that, what's the gradient? If you plot a graph of IL versus that thing to the -1, what is the gradient? IE, right? And the y-intercept is how much? 0, right? So you show it shouldn't pass to the origin. Right? Take your time, plot your graph. That are usually 4 marks or 6 marks. Right? What are you asking for here? I is equal to? Right, so they're talking about the equation for alternating wave, right? So what do you need to get? Right, what is IP? Right, and probably getting omega. 2 pi. Nice. Sketch a graph for 1 cycle. What is the general shape? Alternating, right? 1 cycle, right? When they say 1 cycle, do 1 cycle, right? Don't feel if you do 2 cycles, you get more marks. Right? 1 cycle and put in all the values. Right here, trip velocity. I never, right? And it's all and it makes me the subject, right? What is electron density again? Right? N, which is the number of charge carriers per unit volume, right? Pay attention there. What's the unit for volume here? cm cube, right? So you gotta be careful, right? If you convert to meter cube, or make sure everything else in meters in cm cube. How you convert cm cube to meter cube? Divide by 100 3 times, right? Or divide by 1 by 10 to be -second. Right? You have trip velocity and you have resistivity. What's the formula for resistivity? Right? And then you have your diode junction. You have to draw what happened, right? Right? Or look at under that. Activity, decay constant, and half-life. You all know those things? What about here? How you finding half-life? Right? So you're finding lambda first, and then you're finding half-life, right? Half-life is what? Right? Log 2 on lambda. Make sure you can prove it as well. Here you plot the graph and you linearize something, right? That's it. All right. Right? So same thing I just do there. You all have solutions for those who would have written out everything from crash course and lessons or whatever. Spend some time and go through all the years, go through about 5 years. Right? Within the 5 years, the topics will come back in your year, right in there. So you get information as well. Take about 5 years and look through the answers, right? Have answers all over. Watch them guide you people, watch your videos and watch them do paper out. Right? We're trying to practice, trying to rewrite over all these things, right? Alright,